These everyday meals are built by massive systems running at relentless speed. Behind Dunkin' Donuts, Wendy's, and Pizza Hut are automated mixers, precision grills, and conveyor ovens designed to deliver the same taste millions of times a day. In this video, we go inside the factories to uncover how raw ingredients move through machines to become the fast food you recognize instantly. Dunkin' Donuts production starts with formulation of base dough using a high-capacity spiral mixer. Ingredients are loaded automatically through overhead dispensers connected to silos and tanks. The dry phase includes high-gluten wheat flour, sugar, salt, non-fat dry milk, and dough conditioners. Liquid components include water, whole eggs, vegetable shortening, and yeast. Ingredients enter the mixing chamber in a fixed order to ensure consistency. Flour is dispensed first into the bowl, followed by sugar and salt through calibrated rotary valves. Shortening is pre-melted in a jacketed vessel and dosed into the bowl using a metered pump. Liquid eggs are held in chilled tanks and dispensed through a pneumatic valve. Yeast is hydrated in a separate tank before being introduced into the mix stream. Mixing begins at a low speed to hydrate the flour and form gluten strands. The mixer transitions to a higher speed to fully develop elasticity. Total mixing time ranges between 8 and 12 minutes depending on batch size and target temperature. Bowl temperature is monitored through probes to prevent overheating. Once dough reaches optimal extensibility and temperature, it is discharged into a dough handling conveyor. This conveyor feeds a volumetric divider equipped with servo-driven pistons that portion dough into uniform units. Each portion is shaped into a ball using a rotary rounder. Rounded dough balls are transported by a belt conveyor into a multi-level proofer cabinet. Inside the cabinet, humidity and temperature are controlled to activate yeast fermentation. The dough rests for 30 to 60 minutes based on size and environmental conditions. After proofing, dough pieces exit the cabinet and enter a forming machine configured for ring shapes. A sheeter flattens each piece to a fixed thickness. A dual-blade rotary cutter stamps the dough into rings and removes the center to create the hole. Waste dough is automatically conveyed back to the hopper for reprocessing. Cut dough shapes are placed onto paper-lined proofing trays by a pick-and-place arm. Trays are loaded onto racks that feed into a secondary proofer tunnel. This tunnel maintains consistent humidity and temperature for final rise. Final proofing continues until dough height reaches preset targets. Proofed rings are then transferred onto a mesh belt conveyor leading into the frying system. The fryer is filled with vegetable oil, maintained at 190 degrees Celsius using immersion heating elements. The belt submerges each donut halfway and flips it midway to ensure even browning. Frying time is approximately 90 seconds per side. Excess oil is removed at the fryer exit using an inclined drip section. A vibrating shaker assists in shedding residual surface oil. Donuts proceed to a cooling conveyor that circulates ambient air over the surface to reduce internal temperature before finishing. Cooled donuts are sorted into finishing lines based on type. Plain rings move to the glazing station, which includes a curtain coater that pours warm sugar glaze over moving donuts. Excess glaze is recovered by a recirculation pump. Coated donuts pass under an air knife to remove drips and ensure uniform coating. For powdered sugar varieties, donuts are diverted into a tumbling drum. Fine sugar is dispensed into the drum continuously as donuts rotate inside. The tumbling motion creates full surface coverage. Sugar fines are filtered and reused through a vibratory sifter. Chocolate-coated donuts are transferred to an enrobing line. Melted chocolate compound is maintained at 38 degrees Celsius in a reservoir and pumped to a waterfall applicator. Donuts pass under the waterfall and receive a full coating. An inline cooling tunnel solidifies the chocolate layer. Filled donuts follow a different path. These start as solid discs cut from sheeted dough and proved separately. After frying and cooling, each unit is aligned on a conveyor with a multi-nozzle injection machine. The filling system uses positive displacement pumps to inject jelly, custard, or cream into each donut at a fixed volume. Nozzles penetrate the side and retract automatically after filling. Decorated donuts are moved to a robotic icing station. Each robot arm uses a temperature-controlled piping nozzle to apply icing patterns or toppings. Sprinkles are deposited via gravity-fed hoppers positioned above a vibrating grid. Icing is cooled rapidly with a chilled air tunnel to prevent smearing. Donuts requiring packaging are grouped using a photo eye sensor and placed into trays by a robotic loader. Trays are conveyed to the overwrapping station where a film is wrapped and sealed using a heated jaw. Packaged trays proceed to a labeling machine that applies product and date information. Donuts intended for retail stores are stacked into crates by a pusher arm. Crates are conveyed to a loading dock and stored in temperature-controlled bays before transport. Crate movement is sequenced based on product age to maintain first-in, first-out flow. Throughput is maintained by synchronizing mixing, proofing, frying, glazing, filling, and packing stages. Any discrepancy between steps is corrected by buffer zones built into the conveyor system. Sensors at each handoff point check for weight, position, and spacing. Dough properties are controlled through water temperature, flour hydration, and mixer speed. Yeast activity is adjusted using proofing time and sugar content. Fry color and texture are determined by oil temperature, dwell time, and surface evaporation rate. Glaze thickness is adjusted by flow rate and curtain gap. Chocolate viscosity is controlled with continuous mixing and temperature monitoring. Filling density depends on nozzle diameter and injection pressure. Sprinkle adhesion is determined by icing tack time and coating temperature. Rework dough is monitored to prevent excessive cycles which could affect gluten structure. Oil is filtered continuously through a mesh screen and replenished to maintain performance. Icing and glaze are discarded after exceeding hold time limits. Mechanical components are cleaned using a clean-in-place system for mixers and pumps. Fryer oil is drained and replaced after a fixed number of cycles. Filling stations are purged between flavor changes using heated rinse cycles. Donut size is kept uniform through automated cutting, proofing, and handling. Each unit is weighed inline using load cells before frying. Out-of-spec pieces are rejected by air jets and sent to waste bins. Color is monitored by optical sensors after frying and coating. Each production run is tagged with a digital identifier that tracks every batch of dough from mix to packaging. Operators interface with the line through touchscreen HM is that adjust process parameters and initiate recipe changes. The ring shape is maintained by cutter pressure, proofing time, and dough elasticity. Hollow centers expand predictably when gluten structure and gas production are balanced. Sidewalls form evenly when frying is performed at the correct temperature gradient. Filled donuts expand less during frying due to the absence of a central void. Filling volume is calibrated to prevent leakage and to ensure weight compliance. Injection heads are sanitized between runs using a self-cleaning piston flush system. Production of limited-time donuts uses custom molds or dies fitted to the standard sheeting line. These are swapped in and out using quick-release clamps mounted on the cutting head. All process conditions remain unchanged except for shape and possibly finish. The Dunkin' Donuts production process is defined by sequential control over dough preparation, shaping, frying, finishing, and packaging. No stage is manually operated after initial ingredient loading. All transfers are automated and time synchronized. Mechanical reliability is ensured through routine calibration of volumetric dividers, fryer controls, coating pumps, and injection systems. Sensors detect clogging, misalignment, or loss of temperature and alert the PLC for correction. Air quality around finishing zones is maintained using filtered ventilation that prevents icing contamination. Powder applicators are enclosed and use vacuum returns to contain sugar dust. Chocolate lines are enclosed and climate controlled to prevent blooming. Every donut passes through at least 8 separate mechanical systems before final packaging. Each system modifies dough, temperature, texture, filling, or coating in a defined and repeatable way. The outcome is a donut with precise dimensions, weight, color, and taste profile. Wendy's burgers begin with raw ground beef held in refrigerated stainless steel bins, fitted with auger-driven dispensers. The beef is pre-ground to a fixed particle size and loaded into a hopper positioned above the patty forming system. The patty forming machine uses a hydraulic ram to compress a measured quantity of beef into a square mold. The square mold consists of a cavity with sharp edges and adjustable depth to control thickness. The beef enters the mold vertically and is pressed to a target shape using downward force. A release plate ejects the formed patty onto a conveyor belt lined with a non-stick food-grade belt material. The patties travel on the belt to a pre-cooked staging zone where they are spaced using an optical sensor and gating arm. Each patty is indexed into a clamshell-style contact grill, which applies uniform pressure from above and below. The upper platen is heated with embedded electrical elements and lowered using pneumatic pistons. The bottom platen remains fixed and maintains a set temperature through thermal sensors. Cook time is controlled by belt speed and platen temperature. Average dwell time for each patty is between 100 and 120 seconds, depending on thickness and grill load. Internal patty temperature is monitored using inline thermal probes, which retract automatically after contact. Surface browning is caused by Maillard reactions accelerated by the grill temperature. Rendered fat drains through grooves in the lower platen and is collected in a drip pan. Excess steam is evacuated through a hood system positioned directly above the grill zone. Once cooked, the patty exits the grill and moves onto a staging tray held at a constant holding temperature using a heat lamp array. While patties are cooking, buns are prepared on a separate toasting line. Buns arrive from storage in trays and are unloaded onto a conveyor. The bun separation system uses rotating paddles to split top and bottom halves and align them face down on the line. Each bun half passes under a radiant toaster element, which operates at a fixed distance above the surface. Toasting time is determined by conveyor speed and element intensity. Bottom buns are toasted slightly longer than top buns to handle moisture from toppings. After toasting, buns proceed to the assembly belt where they meet other components. Burger toppings are prepared on parallel preparation lines. Leaf lettuce is pre-cut and washed, then stored in chilled bins and dispensed manually into bins along the line. Tomatoes are sliced using a rotary blade slicer that maintains uniform thickness. Slices are collected into trays and moved to the topping line by belt conveyor. Onions are peeled and cut using an automated ring slicer and loaded into shallow pans. Pickles are pre-sliced and held in brine-filled containers until use. Cheese slices are separated by a vacuum picker and fanned out onto a chilled tray. Condiments, including mayonnaise, ketchup, and mustard, are dispensed using trigger-activated pumps that release a fixed volume per stroke. Dispensers are calibrated to deposit evenly without spread beyond the bun area. Burger assembly begins with bottom buns moving along a belt aligned with the topping line. A pump dispenses mayonnaise directly onto the bun in a circular pattern. A square cooked patty is placed onto the bun using a precision-guided placing arm, or manually depending on station configuration. Cheese slices are placed directly on top of the hot patty, which softens the cheese slightly but does not fully melt it. Sliced tomato is added next by tongs or fingers placed at center alignment. A leaf of lettuce is layered over the tomato and adjusted to not overhang the bun. Onion rings are laid flat across the lettuce with no stacking. 2 or 3 pickle slices are placed side by side depending on diameter. Ketchup and mustard are dispensed in zigzag or dot patterns based on the specific burger recipe. The top bun is retrieved from its place on the parallel conveyor and inverted onto the built stack using a rotating arm. The complete burger is then moved forward to a wrapping station where it is enveloped in printed foil or wax paper. Wrapping is done by folding each side toward the center and then folding the base upward before rolling the package forward. Wrapped burgers are placed into holding bins arranged by product type. Bin trays are heated from beneath with radiant elements to hold temperature. Burger names and identifiers are shown on digital displays above each bin. The wrapped burgers are then pulled in the order of assembly requests from service or drive-through lines. For specialty burgers with additional ingredients, separate modules are added to the line. Bacon is pre-cooked in convection ovens and held on heated trays. Spicy toppings or sauces are dispensed through separate triggers. Extra patties are added by adjusting tray positions to align multiple cooked patties before final topping. The entire burger line is modular and designed for high throughput. Each step, from toasting to wrapping, is timed and paced using conveyor intervals and operator rhythm. Cooked patties are used within a fixed window to maintain thermal properties during assembly. The square patty shape aligns precisely with the round bun through placement guides. Cheese coverage is optimized by placing the slice diagonally across the square patty. Lettuce folds are standardized to reduce overhang and dripping. Tomato slices are inspected visually for diameter and replaced if undersized. Onions are separated into ring layers to maintain consistent thickness. Pickles are spaced to prevent overlap or bunching. Sauce volumes are adjusted using pump restrictors. Each pump cycle delivers a metered dose that is verified weekly by weight checks. Dispense angles ensure center placement with minimal deviation. Top bun pressure is measured periodically to confirm compression does not exceed tolerance. Overcompression can cause lettuce or tomato slippage. Wrap tightness is checked by torsion testing with digital force gauges. Grill platen pressure is balanced to avoid sear marks that penetrate too deeply. Contact time is calibrated to match patty water content and surface heat conductivity. Belt tension is maintained through spring-loaded rollers at both ends of the grill. Drip pan contents are filtered and cooled before disposal. Grease flow is measured to calculate fat loss per batch. Each tray of patties is weighed at intervals to confirm moisture retention and yield. Conveyor speed is set to match maximum output per cook zone. Bun toast time is synchronized to meet grill exit timing. Topping replenishment occurs based on tray weight thresholds detected by load cells. Tomato and onion prep stations are cleaned and reset every few cycles to prevent buildup. Cheese trays are kept below 5 degrees Celsius using chilled gel plates. Lettuce bins are sloped for continuous access without compaction. Burger stacking alignment is controlled by operator training and guided bins. Variants like double burgers use the same assembly line with secondary patty placement after cheese. Burgers with spicy or grilled ingredients use segregated stations to prevent flavor transfer. All process parameters are displayed on line-side screens for real-time monitoring. Operators adjust pump pressure, toast speed, and tray positions based on on-screen instructions. Each station is time-stamped to maintain consistency across shifts. Ingredient freshness is managed by rotation schedules and bin timers. No topping remains in use beyond its designated holding time. Each component has a separate preparation and service life which governs when trays are replaced. The square patty ensures uniform cooking and reduces edge shrinkage. Griddle contact area is maximized by flat pressing. Consistent doneness is achieved across all patties through center-out thermal profiles. The full Wendy's burger is formed by layering precise ingredient units in defined order. Each addition is made at a fixed position along the conveyor. The sequence ensures balance in flavor, weight, and thermal distribution. Assembly line pacing is regulated by burger type, quantity, and order load. Stack height is limited by bun compression threshold. Burgers are finalized within a tight time window to maintain optimal serving temperature. Pizza Hut. Pizza production begins with the preparation of pizza dough using automated high-capacity mixers. Each batch starts with high-protein wheat flour dispensed from overhead silos through a pneumatic conveyor into a stainless steel mixing bowl. Water is metered precisely from a temperature-controlled supply line and delivered into the bowl through solenoid valves. Instant dry yeast is stored in sealed bins and dispensed by auger into the bowl after water. Salt and sugar are pre-weighed and released into the bowl from vibratory feeders mounted above the mixer. Vegetable oil is pumped from a storage tank through a heated line and added last to ensure uniform distribution. The spiral mixer begins in a slow speed mode for 1 minute to hydrate the dry ingredients. After hydration is complete, the mixer shifts to high speed to develop gluten structure. Mixing continues for 8 to 10 minutes until the dough reaches a defined elasticity and target temperature range. The dough is discharged into a trough and transferred to the divider using a hydraulic lift arm. The divider uses a piston system to cut dough into fixed weight portions based on pizza size specifications. Each dough piece is rounded into a ball shape by a rotary rounding mechanism and deposited onto a lightly floured tray. Rounded dough balls are conveyed into a temperature and humidity-controlled proofing cabinet. The proofing stage allows yeast fermentation to produce gas and relax the dough structure. Temperature is held around 38 degrees Celsius and humidity near 85% to maintain surface softness. After proofing for approximately 1 hour, the dough is moved to a pressing station. Each ball is loaded onto a heated platen, which presses the dough into a disc shape. Pressing is done with a hydraulic top plate that flattens the dough to a specified diameter and thickness. Heat from the platen sets the shape and prevents shrinkage during later handling. Pressed dough discs are transferred to perforated baking pans or screens using a vacuum lifter. A light mist of oil is applied to the pan surface to prevent sticking. The dough and pan then move along a conveyor to the topping line. Topping application begins with sauce deposition using a volumetric piston filler. The sauce is pumped from a heated holding tank and dispensed in a spiral pattern starting from the center of the dough. A rotating disc beneath the pizza ensures even coverage without manual spreading. Shredded mozzarella cheese is stored in chilled hoppers and fed to a depositor via a vibratory conveyor. Cheese is distributed through rotating paddles that drop a measured weight evenly across the surface. Cheese coverage is calibrated to stay inside the dough border. Additional toppings are added in a fixed sequence depending on pizza type. Pepperoni slices are dispensed from a rotary carousel that places overlapping slices in concentric rings. Cooked sausage crumbles are metered through a hopper with a gate-controlled release. Vegetable toppings such as mushrooms, green peppers, and onions are added from separate hoppers using calibrated volumetric scoops. Bacon pieces and ham strips are dispensed from compartments, lined with agitators to prevent bridging. Olives are dropped from a chute fitted with a shaker plate to ensure even distribution. Pineapple chunks are added last and drained before dispensing to avoid excess moisture. Each pizza proceeds to the oven loading belt, which is synchronized with baking time and oven speed. The pizzas enter a conveyor oven with a stone or mesh belt and a controlled baking chamber. Top and bottom heat are separately adjustable using electric elements or gas burners. Baking time is generally between 6 and 7 minutes, depending on pizza size and topping load. The oven is divided into thermal zones, which apply different temperatures to optimize crust and topping finish. Air circulation fans maintain uniform heat distribution within the chamber. Crust browning is controlled by bottom belt temperature and pan contact. Cheese melt is regulated by top zone intensity. Sauce bubbling and topping cooking are completed within the dwell time set by conveyor speed. Once baking is complete, the pizza exits the oven and is transferred onto a staging table with a heat-resistant surface. A metal lifter is used to remove the pizza from the baking pan if one was used. The pizza is then slid onto a cutting board positioned below a rocker blade cutter. The cutter is hinged to apply uniform downward pressure and is guided by slots in the board to maintain equal slice sizes. Standard cut configurations are 4, 6, or 8 slices depending on diameter. Each pizza is rotated to complete perpendicular cuts if required. Cut pizzas are transferred onto corrugated cardboard discs which serve as a support base. The pizza and disc are inserted into printed boxes by a sliding motion, which prevents topping displacement. Boxes are closed with a fold lock mechanism and stacked in batches on a heated shelf for holding. Specialty pizzas with cheese-stuffed crust use a different pressing process where cheese sticks are inserted into the dough edge before sealing. The dough is crimped mechanically to enclose the cheese along the perimeter. These variants are baked with slightly longer dwell times to ensure cheese softening. Thin crust pizzas skip the proofing stage and are sheeted directly after mixing. The sheeting line flattens dough using a 3-stage roller system that progressively reduces thickness. Sheeted dough is cut to shape using a rotating die and docked to prevent bubbling. It is transferred directly to the topping line without additional rise. Pan pizzas use thicker dough portions which are hand-pressed or machine-pressed into deep pans coated with oil. The oil creates a fried base texture during baking. These pans are baked longer at lower temperatures to prevent surface burning. Pizza Hut production lines are modular and can run multiple styles concurrently by using different lanes. Each lane is fed by a shared dough room and topping prep area. Toppings are staged in mobile chilled carts that are swapped based on menu rotation. Sauce preparation occurs in a separate area where tomato concentrate is blended with water and seasoning. The sauce is cooked in steam kettles and cooled rapidly before being pumped to holding tanks. Cheese is shredded in-house using rotary drum shredders or received pre-shredded in lined totes. Toppings are prepared using a combination of manual and automated methods. Whole vegetables are washed and sliced on rotating blade machines. Meats are pre-cooked and diced using high-speed dicers or crumblers. Toppings are loaded into color-coded bins and inserted into the topping line feed hoppers. Ingredient flow is monitored by load cells under each hopper, which signal refill triggers when weight drops below threshold. Each depositor is linked to a PLC that controls dispense rate, duration, and alignment. Pan and tray washing systems clean and sanitize bakeware after each use. Washed pans return to the pressing line in timed cycles. Conveyor belts are brushed and wiped at shift intervals to remove topping residue. All components of the pizza undergo mass balance verification to ensure recipe compliance. Each pizza's final weight is checked on a dynamic scale before boxing. Deviations trigger visual alerts and operator review. Conveyor speeds, depositor timing, oven temperatures, and cut configurations are all adjustable by touchscreen interfaces mounted on each station. Operators select pre-programmed recipes which load all parameters automatically. The dough formulation is calibrated to yield consistent rise, chew, and browning under standard conditions. Oil content determines tenderness, while yeast quantity controls gas production. Mixing temperature is adjusted based on flour temperature and ambient conditions to ensure batch uniformity. Cheese melt properties are influenced by moisture content and shred size. Sauce consistency affects spreadability and absorption into the dough. Topping order ensures base ingredient contact with heat for proper cooking. Every Pizza Hut pizza follows a defined flow from dough to boxed product. Each process stage adds a functional component that determines structure, flavor, or visual finish. Assembly is done in linear progression with limited manual input beyond topping reload and box stacking. Pizza format changes involve reconfiguring press molds, pan shapes, and depositor settings. Crust variants, such as garlic butter infused or herb seasoned, are handled by adding a post-bake brushing stage, where liquid toppings are sprayed onto the crust using a rotating nozzle arm. Pizzas with drizzle finishes or sauces applied after baking use a dedicated finishing table where squeeze bottle applicators or peristaltic pumps add final ingredients. These finishes are applied before boxing and allowed to set for several seconds. Temperature retention in boxes is enhanced by vent hole design, box material thickness, and stacking method. Pizza integrity during transport is preserved by maintaining alignment and minimizing topping shift through controlled insertion angles. The production of Domino's Pizza begins not in the store kitchens, but in massive regional supply chain centers, where the ingredients, particularly the dough, are produced in industrial quantities with an emphasis on consistency, quality, and efficiency. Before any pizza reaches the oven in a Domino's franchise, it starts its journey in these highly controlled factory environments where each element is formulated to exact specifications. The first and most critical component is the dough, which is made fresh daily in these centers and delivered under cold storage conditions to every Domino's outlet. The dough making process begins with the arrival of bulk ingredients, including high-protein wheat flour, water, vegetable oil, yeast, sugar, and salt. These ingredients are stored in separate storage systems based on their physical state and volume requirements. Flour is kept in massive silos connected to the production floor through pneumatic tubing systems. These tubes transfer flour directly into the industrial-scale mixers with precise weight measurements, controlled by automated batching systems. Water, which must be maintained at a specific temperature range to activate the yeast properly, is stored in stainless steel tanks connected to digital flow meters. This ensures the exact volume is dispensed into each batch, typically to within 1/10 of a liter. Vegetable oil, sugar, salt, and yeast are also dispensed through closed-loop systems that prevent contamination while ensuring high-speed delivery and accuracy. The industrial mixers used at this stage are horizontal high-capacity spiral mixers or fork mixers, depending on the location and the specific equipment model in use. Each mixer is designed to handle hundreds of pounds of dough per batch, usually around 400 to 600 pounds. The process begins with dry ingredients being added first, followed by a controlled stream of water and oil. Once the mixture reaches the desired hydration point, the mixer operates at different programmed speeds to knead the dough until it reaches the correct elasticity and gluten development. This usually takes around 8 to 10 minutes, with temperature sensors embedded in the bowl to prevent overheating from friction, which can damage the yeast. As the dough mixes, factory floor operators monitor each batch's time, temperature, and consistency through a computerized interface. Every mixer is part of a larger manufacturing execution system that records batch data, ingredient lots, timestamps, and operator IDs. This traceability system ensures that if a problem ever arises, such as inconsistent rise or poor texture in a batch, managers can track it back to the specific flour lot or mixing time and make necessary adjustments for future runs. Once the dough reaches optimal consistency, it is automatically discharged from the mixer into a dough trough, which is essentially a wheeled stainless steel container that holds the dough until it's moved to the dividing station. The dough is then transferred into a hopper above a hydraulic or rotary dough divider. This machine uses either vacuum-assisted suction or mechanical cutting blades to portion the dough into uniformly weighted balls, typically ranging from 6 to 20 ounces, depending on the final pizza size. Each portion is measured by load cells, digital weighing systems that maintain accuracy within a few grams. These dough balls then proceed to the rounding machine, which takes each divided piece and rolls it into a tight, smooth sphere. This is crucial for creating the internal tension needed for a uniform rise during fermentation. The rounding machine uses rotating plates or belts that apply gentle pressure and a circular motion to the dough. After rounding, the dough balls are dusted lightly with food-grade flour or semolina to prevent sticking, and then placed into oiled dough trays. These trays are stacked and covered with plastic lids or wraps to maintain humidity and prevent surface drying. They're labeled with a printed barcode that includes the production date, time, dough type, and batch number. At this point, the dough enters the proofing phase, which is critical to developing both the structure and flavor of the final pizza base. Proofing occurs in temperature and humidity-controlled rooms, where racks of dough trays are stored for several hours. The ideal proofing conditions are generally around 80 degrees Fahrenheit with 75% relative humidity, although this can vary slightly based on factory location and yeast activity. The yeast begins to consume the sugars in the dough, producing carbon dioxide and ethanol as byproducts. This gas becomes trapped within the dough's gluten network, causing it to expand and develop the characteristic airy, chewy structure. Simultaneously, organic acids and alcohols created during fermentation start to build complex flavor notes in the dough. During the proofing period, plant operators conduct regular checks to monitor dough expansion, surface tension, and even internal temperature using infrared thermometers and visual inspection. Some factories use automated camera systems that scan the trays and calculate proofing progress by measuring the dough's rise and dome shape. Any deviations from the standard profile are flagged for intervention, whether that means extending the proofing time or moving certain trays to a different section of the proofing room. Once the dough reaches the desired level of fermentation, it is moved to the cold storage phase. In this stage, the dough trays are rolled into large walk-in refrigeration rooms, where the temperature is maintained at approximately 2 to 4 degrees Celsius. This halts the yeast's activity and locks in the developed flavor while also preventing overproofing. The chilled dough can now be stored for up to several days, depending on demand at the destination stores. During this time, the trays are rotated to maintain even cooling and are occasionally inspected for signs of over-fermentation or drying. While the dough is being prepared, Domino's is also handling the sauce production in parallel. Tomato sauce is made in separate processing areas, using high-volume stainless steel kettles equipped with agitators and heating jackets. The base of the sauce is tomato paste, which is diluted with water to reach a specific consistency. To this, measured quantities of salt, sugar, oregano, garlic, basil, black pepper, and other proprietary spices are added. Some locations use pre-mixed spice sachets that are batch-coded for accuracy, while others blend the seasoning on-site. The sauce mixture is heated to temperatures between 80 and 90 degrees Celsius to sterilize it and meld the flavors. Once the heating process is complete, it is rapidly cooled using a plate heat exchanger to bring it down to refrigerated storage temperature, usually 30 degrees Celsius, around 4 degrees Celsius. The cooled sauce is then transferred into food-safe storage containers, often in 10-liter or 20-liter units, and sealed with tamper-evident caps. Each container is labeled with a batch code and production date before being staged for shipment alongside the dough. In addition to sauce, the factory prepares other key ingredients, including shredded cheese and select toppings. The cheese used in Domino's pizzas is typically a low-moisture mozzarella, known for its excellent melting properties and stretch. Some supply centers receive the cheese in bulk blocks and shred it in-house using high-speed rotary shredders that slice the blocks into uniform strands. The shredding process includes a light coating of anti-caking agents like potato starch or cellulose to prevent clumping during storage. The shredded cheese is packed into portioned bags, vacuum sealed, and stored under refrigeration. Once all ingredients, dough, sauce, cheese, and prepped toppings are ready, they are organized and loaded into refrigerated delivery trucks. These trucks operate under a tight logistics schedule, making daily or multi-day trips depending on the volume needs of each Domino's franchise store. The internal temperature of each truck is continuously monitored using GPS-integrated data loggers, and real-time data is fed back to the supply center's central operations system. This ensures that if any deviation in temperature or route timing occurs, corrective action can be taken immediately. By the time the products arrive at the store, they are fully prepared and only require assembly and baking. The franchise stores then execute the final steps of pizza preparation, which involves pressing out the dough, saucing, topping, baking, and packaging. However, the factory's role is absolutely central to ensuring that every ingredient arrives at the exact same standard, no matter where the pizza is being made or consumed. Through this centralized and automated model, Domino's achieves consistency at a global scale, while minimizing waste and human error in the earliest and most foundational stages of production. Once the refrigerated trucks deliver the dough, sauce, cheese, and toppings to each Domino's franchise, the handling of those ingredients transitions from centralized factory production to carefully structured in-store processes that continue to follow standardized protocols. However, the factory's influence is far from over at this point. The store-level procedures are engineered to mirror the consistency, precision, and speed found in the supply chain centers, effectively extending the factory environment into each retail location. Inside the store, the first critical action is the proper storage of the dough. As the dough trays arrive straight from cold storage, they are transferred into the store's walk-in refrigerator, where they are kept at a consistent temperature of 2 to 4 degrees Celsius. Each dough tray remains sealed with its identifying barcode, which includes the production batch, date, and shelf life. This code is scanned upon arrival, logged into the store's inventory system, and linked to the store's daily forecast so the staff can prioritize older dough for earlier use, following a strict first in, first out system to ensure freshness and prevent waste. Before the dough can be used for making pizzas, it needs to temper. Cold dough straight from refrigeration is too stiff and contracted to stretch evenly or bake correctly. Therefore, several trays are pulled from the cooler in staggered intervals and placed in a proofing area within the store, typically kept at room temperature for 30 to 60 minutes. During this period, the dough relaxes, allowing the gluten to become more extensible and the yeast to reawaken slightly, which enhances browning and flavor development in the oven. This step also restores some of the softness and elasticity necessary for the dough to perform consistently on the preparation line. The next key phase in the process is dough pressing or hand stretching, which transforms the proofed dough ball into a pizza base. Depending on the store's equipment and regional preferences, Domino's uses one of several standard methods for this. In many high-volume locations, a mechanical dough press is employed. This press is a heated platen system where a single dough ball is centered between two metal plates. With controlled pressure and temperature, the plates compress the dough to the specified diameter and thickness. The brief heat exposure also helps to set the edge of the crust slightly, which prevents overexpansion during baking. Other stores use hand stretching techniques, which involve manually flattening the dough using the palms and fingertips to create an even disc, often followed by a gentle spinning motion to widen it to the correct diameter. Employees are trained to feel for even dough resistance, check the uniformity of thickness, and ensure the edges are slightly thicker to create the signature Domino's crust ring. Some locations employ a dough sheeter, a machine that flattens dough between two adjustable rollers, which is commonly used for medium thickness crusts or thin crust options. Once the dough is properly shaped and placed on a pizza screen or baking tray, it is ready to be sauced. The sauce comes in pre-measured containers or large bag-in-box systems with pump dispensers, depending on the store's volume. A standardized rotary sauce ladle or domed saucer is used to apply a precise amount of sauce, usually between 90 and 120 grams for a medium pizza. The sauce is spread using a circular motion that stops approximately 1 inch from the crust edge to allow for natural bubbling and rim development during baking. With the base sauced, the next step is the cheese application. Domino's cheese is a proprietary, low-moisture mozzarella blend, optimized for melt, stretch, and browning. The cheese arrives shredded in sealed, chilled bags and is stored in under-counter refrigeration near the prep stations for quick access. Employees use color-coded scoops to portion out exact grams of cheese per pizza size: small, medium, large, or extra large. This consistency ensures that the cheese melts evenly and that the nutritional and caloric values remain standardized. In high-throughput stores, preloaded portion dispensers or weigh scales may also be integrated into the cheese station to reduce time and improve accuracy. Next, the pizza moves to the topping stage. Domino's toppings, such as pepperoni, Italian sausage, mushrooms, green peppers, onions, olives, jalapenos, grilled chicken, and bacon, are kept in ingredient rails with stainless steel pans, maintained at safe refrigeration temperatures using undermounted chillers. Each topping has a designated scoop or set of tongs, and employees are trained to apply the correct amount and distribution per pizza size and recipe. Toppings are applied in a set sequence to ensure even cooking and consistent flavor layering. For example, pepperoni slices are laid edge to edge to cover the surface in a signature circular pattern, while sausage crumbles are more scattered to allow airflow between pieces. Vegetables are typically added last, as their moisture content can impact the crispness of the crust if layered too deeply. Domino's uses laminated guides and portion charts to ensure that every pizza, regardless of who's preparing it, looks, weighs, and tastes the same. With the pizza fully assembled, it is placed onto a conveyor belt oven, also known as an impingement oven. This oven style uses jets of superheated air blasted from top and bottom to ensure even baking. The oven belt is set to a precise speed, generally resulting in a 5.5 to 7 minute bake time, depending on the pizza size and topping density. The oven's digital interface allows staff to select different profiles for thin crust, hand-tossed, deep dish, or extra cheese options. Each profile adjusts air velocity, top and bottom heat ratio, and belt speed to produce the ideal bake for that style of pizza. During baking, several chemical and physical transformations take place. The crust expands slightly from the final stage of yeast fermentation. Steam is released from the sauce and toppings, and the cheese melts and begins to brown through the Maillard reaction. Excess moisture from vegetables is evaporated by the oven's airflow, ensuring the crust remains crisp and doesn't sag. The pizza emerges from the other side of the oven, fully baked and ready for slicing. At the end of the conveyor, pizzas are transferred to a staging counter, where they rest for 20 to 30 seconds to allow the cheese to set slightly. Then, using a rocker blade or circular pizza cutter, employees cut the pizza into standard portions, usually 8 slices for a large pizza, based on Domino's cutting guides. Each pizza is then slid into a branded corrugated cardboard box, which is specially designed with vent holes and moisture-absorbing liners to preserve crispness during delivery. Every box is sealed and receives a printed label generated by the store's order management system. This label includes the customer's name, order number, timestamp, and pizza specifications. For orders placed online or through the app, this also triggers an update on Domino's proprietary pizza tracker, which uses real-time data from kitchen sensors to notify customers of each stage, from dough prep to oven entry, baking, boxing, and out for delivery status. Throughout the day, all these processes are monitored for compliance with Domino's global standards. District managers conduct regular audits using detailed checklists covering dough handling, oven cleanliness, bake quality, topping accuracy, and safety procedures. Additionally, Domino's has built-in kitchen timers and alert systems that ensure no dough is held at room temperature too long, no pizzas sit unboxed beyond the quality threshold, and no ingredients are used past their hold times. Each store's operations are built to match the precision and consistency of the supply chain factories. In fact, many stores undergo periodic retraining sessions to realign their practices with the upstream factory procedures. This ensures that no matter how far the finished product is from the centralized dough production, the final experience to the consumer remains nearly indistinguishable between one location and the next. As soon as a Domino's pizza is sliced and boxed, the journey continues into a carefully engineered phase focused on preserving product quality and maximizing delivery efficiency. At this point, what might appear to the customer as the simple act of putting a pizza in a box and sending it out the door is, in reality, a continuation of Domino's factory-grade systems, refined, tracked, and executed with industrial precision. Each Domino's box is made of specially designed corrugated cardboard, engineered not only to be structurally strong enough for stacking and transportation, but also to allow moisture control and thermal retention. Small vent holes are strategically placed around the box edges to allow steam to escape without sacrificing internal heat. This is critical to maintaining a crisp bottom crust while keeping the cheese and toppings hot and intact during transit. The liners inside some specialty pizza boxes also use grease-resistant coating and moisture-wicking micro layers that reduce sogginess, especially in pizzas with heavier vegetable or meat toppings. Once the pizza is placed in its box, a label is immediately printed and applied. This label contains all relevant details: the order number, pizza type, time of bake, the customer's name and address, and specific cooking instructions if applicable, like extra crispy crust, light sauce, or no cheese. More importantly, the label also includes digital timestamps and batch codes that tie the finished product directly back to every earlier phase of production. These codes link the order to its dough batch, sauce mix, cheese lot, and even the name of the employee who boxed it. This allows full traceability, and in the event of a customer complaint or quality issue, managers can pull up detailed records to investigate and resolve the problem efficiently. The next link in the process is the delivery system, which Domino's has industrialized to a level similar to its supply chain and production operations. Every Domino's location uses a centralized digital system to optimize delivery routes, monitor driver location, and track pizza temperature using estimated time-to-door algorithms. In some urban areas or flagship locations, Domino's even uses thermal sensors and GPS modules in the delivery bags themselves. These sensors ensure that the pizza never drops below the acceptable temperature threshold, typically around 140 degrees Fahrenheit or 60 degrees Celsius, which maintains cheese integrity and topping stability. The delivery bags used are not basic insulated containers. They are purpose-built thermal sleeves with advanced insulation material, sometimes incorporating phase change materials that hold heat without overheating the product. These bags are lined with aluminum and closed with Velcro or zippers to ensure no heat escape. In some pilot programs, Domino's has experimented with electrically heated delivery pouches that plug into the vehicle's charging outlet, maintaining a regulated temperature across the entire delivery window, especially in colder climates. While the pizza is en route, Domino's proprietary pizza tracker remains active. This cloud-based interface receives inputs from multiple sources: the POS system, kitchen sensors, label printer, and delivery dispatch terminal, and creates real-time updates for the customer. As soon as the order is marked out for delivery, a countdown begins based on predictive delivery timing, factoring in distance, time of day, historical traffic data, and driver availability. This transparency not only improves customer satisfaction, but also provides performance data for internal use. Behind the scenes, Domino's aggregates all this operational data into their enterprise-wide performance dashboards. Each store's key performance indicators, such as order accuracy, delivery time, baking efficiency, and customer satisfaction scores, are updated daily. Store managers and regional supervisors review these metrics in regular meetings, identifying trends, deviations, and opportunities for improvement. If a certain franchise location consistently shows slower bake times or increased complaints about cold pizza, it may trigger a maintenance review of the oven system or retraining of kitchen staff. Meanwhile, at the supply chain level, Domino's uses reverse logistics to complete the factory-style loop. Once a delivery is completed, used ingredient bins, dough trays, and empty sauce containers are returned to the regional supply centers on the next inbound truck trip. These items are cleaned, sanitized, and reused according to food safety protocols. Reusable dough trays, for example, go through automated washing systems that use high-pressure jets, detergent, and thermal sanitation to prepare them for the next production cycle. By managing both outgoing and incoming flows efficiently, Domino's minimizes waste and maximizes logistical efficiency, keeping the system sustainable and cost-effective. Beyond the visible kitchen and delivery operations, there is also a sophisticated forecasting and inventory management system that relies heavily on factory data. Using AI and machine learning, Domino's forecasts demand for dough, sauce, cheese, and toppings at each store based on variables like local events, weather, historical order volumes, and even social media trends. This information is transmitted back to the supply chain centers, which adjust dough production and ingredient packaging accordingly. For example, if a city is expecting a snowstorm, the system may predict a spike in delivery orders and increase dough production by 10% for the affected stores. This tight integration between forecasting and factory production minimizes spoilage and overproduction, ensuring that only as much dough and sauce is produced as will be used within a defined freshness window. The same logic applies to toppings and cheese. Ingredients that are nearing the end of their shelf life can be flagged automatically, prompting store managers to run promotional offers or bundle deals to encourage faster turnover. By linking the retail environment back to the factory floor, Domino's achieves a level of responsiveness and precision rarely seen in traditional food service operations. Domino's also incorporates periodic updates and R&D feedback into its manufacturing systems. When a new product is launched, such as a specialty crust or a new line of toppings, the manufacturing centers adapt their formulations and packaging processes to accommodate the change. For instance, a new crust option may require a dough with a different hydration level or proofing profile. In that case, dough mixers are recalibrated, proofing room settings adjusted, and additional QA steps introduced. The product launch timeline includes upstream changes that affect every supply chain center, down to the labeling system and transport logistics. To maintain global brand consistency, Domino's has standardized its production protocols across all countries. yet also incorporates regional customization. For instance, the dough produced in India may include slight formulation changes to better suit local humidity levels or flour types. In Japan, where crust styles vary, dough mixing and resting procedures may be adapted for fluffier or rice-infused bases. However, the core manufacturing principles, precise batching, automated mixing, cold chain delivery, and digital inventory tracking, remain consistent regardless of geography. Domino's also performs routine auditing and calibration of their supply chain centers to ensure continued alignment with performance standards. Factory equipment such as mixers, dividers, and temperature control units are subjected to preventive maintenance and calibration checks at regular intervals. Technicians verify dough density, elasticity, and yeast activity using physical measurements and digital readouts. Similar checks are done for sauce viscosity, cheese fat content, and topping moisture levels. These numbers are logged and analyzed to identify any drift from target specifications, allowing corrective measures to be implemented before product quality is affected. Even packaging materials go through quality control. Corrugated boxes are tested for burst strength, fold endurance, and thermal retention properties. Adhesives used for box sealing are food safe and resistant to temperature extremes. The printing quality on labels is monitored to ensure clarity and durability, as these labels serve both customer-facing and internal traceability functions. Everything down to the ink used on packaging is selected for durability under heat and moisture, a testament to the factory-level thinking that permeates the entire Domino's ecosystem. KFC's fried chicken may be iconic for its secret blend of 11 herbs and spices, but the factory process behind every crispy, golden piece is built on something far less mysterious: precise engineering, timed workflow, and ruthless consistency. Behind every bucket of original recipe is a production line designed to turn raw chicken into seasoned, breaded, and pressure-fried perfection on a massive global scale. Millions of pieces per day across thousands of locations, all starting in high-throughput poultry processing facilities. The process begins at the poultry plant, long before any chicken sees a fryer. KFC doesn't raise its own chickens. Instead, it partners with large-scale poultry suppliers who specialize in high-efficiency, vertically integrated operations. These facilities process thousands of birds per hour using lines that are fully automated and regulated to deliver uniform size, weight, and quality. Once chickens arrive at the facility, they're stunned and humanely slaughtered, then passed through defeathering machines. The birds are washed, eviscerated, and chilled in cold water or air-chilling tunnels, depending on the region and regulatory requirements. From here, they move to automated cutting lines, where high-speed blades segment each bird into standardized cuts: drumsticks, thighs, wings, and breasts, with specific sizing tolerances so each piece will cook evenly during pressure frying. Every piece is trimmed and inspected, then sent through water jet portioning systems, lasers, and nozzles that precisely cut meat based on optical sizing. Pieces are sorted by weight to ensure uniform cook times, then chilled to below 40 degrees Fahrenheit and packed in vacuum-sealed bags. These raw chicken portions are shipped to regional KFC prep centers or directly to KFC kitchens, depending on location. At centralized KFC prep facilities, often located near urban hubs or distribution centers, the real transformation begins. Here, each piece of raw chicken is thawed, if frozen, washed, and carefully inspected again. Workers wear full food-safe suits, gloves, and hairnets, operating under strict HACCP protocols to avoid cross-contamination. Every batch is handled in cold prep rooms, where the air is chilled and filtered to keep bacterial growth to a minimum. Then comes the marination phase, a foundational step in the flavor and texture of KFC's chicken. Each piece is soaked in a liquid brine, typically a mix of water, salt, phosphate, and other flavor-carrying compounds. The phosphate acts as a moisture-retaining agent, helping the chicken stay juicy through frying. This brine is vacuum tumbled into the meat using large rotating drums, which massage the liquid deep into the muscle fibers over the course of 30 to 60 minutes. Every load is weighed before and after to ensure absorption is within spec. Next comes seasoning. Contrary to myth, the famous 11 herbs and spices are not mixed at every location. Instead, the spice blend is produced at a secure, centralized facility where the exact combination is pre-measured and packed into coated, tamper-proof bags. These bags are shipped to prep centers or stores where they're added directly to flour for the breading process. Only a few people in the company know the full recipe, and the factory itself is designed to prevent accidental or deliberate disclosure. Even the workers handling the blend often don't know what's in it. In the prep facility, seasoned breading stations are set up in long rows where chicken moves through the legendary hand breading process. Each piece is dredged in seasoned flour, then placed in a shallow basket where it's pressed into the flour with a very specific folding and compression motion. This step, called the 7-10-7 method, is taught to every KFC cook and replicated in prep facilities worldwide. It's part of what gives KFC chicken its craggy, crunchy, uneven texture. The breaded pieces are then loaded onto trays and either flash chilled for shipment or sent directly to in-house kitchens for frying. In some markets, partially cooked chicken is sent to stores to shorten fry times during service rushes. But in most regions, frying is done fresh in-store, using the same tightly controlled procedure. In KFC restaurants, pressure fryers are the beating heart of the operation. These aren't just deep fryers, they're sealed, industrial pressure cookers that fry chicken under high pressure and temperature. The typical fryer operates at around 350 degrees Fahrenheit under 12 psi, allowing the chicken to cook faster and retain more moisture than open frying. The result? A crisp exterior with a tender, juicy interior, cooked in about 10 minutes per batch. Each piece is loaded into a wire basket or chicken clamshell, arranged in a way that ensures even oil flow. The basket is locked into the fryer, the lid is sealed, and the cook cycle begins. Once complete, the fryer releases pressure and the basket is lifted. Every batch is placed on a draining rack, where oil drips off and the crust sets. From there, chicken is either held in warming cabinets kept at a specific humidity and temperature, or served immediately, depending on demand. Quality checks are frequent. Staff use thermometers to confirm internal temperatures, visual checks to verify color and breading coverage, and taste tests to ensure consistency. Any batch that sits too long is discarded to maintain quality standards. Back in the prep centers, not all chicken ends up as original recipe. KFC also produces extra crispy, spicy, and grilled varieties, each requiring slightly different breading and cooking profiles. Extra crispy chicken, for instance, goes through a double breading process with a coarser flour blend and is fried in open fryers, not pressure ones. The breading station must be cleaned and reset between batches to avoid cross-contamination between flavors. Meanwhile, grilled chicken is seasoned differently, rubbed with a dry spice mix and roasted in combi ovens, not fried at all. These ovens use steam and convection to cook the meat evenly while keeping it juicy. The flavor is more subdued, but the factory process behind it is just as strict, with marination and seasoning steps done under cold room conditions before transport. Throughout the entire system, data is king. Every batch of chicken, from farm to fryer, is logged with timestamps, location codes, and supplier data. Digital systems track everything from fryer oil turnover rates to breading mix usage, ensuring that no store deviates from standard operating procedures. Even the oil itself is filtered between batches and replaced on a tightly controlled schedule. Sensors monitor fryers for temperature drift and alert staff if anything strays outside of spec. Sanitation is constant. Between batches, breading stations are cleaned, gloves are changed, and utensils are sanitized. The entire prep room in a factory is stripped down at the end of each shift and pressure washed with food-grade disinfectants. Air in the facility is filtered and recirculated to control temperature and humidity. Workers follow strict entry protocols, passing through air curtains and sanitizing stations before handling any food. And while the public rarely sees it, KFC's factory network is global but highly localized. Facilities are located close to supply chains and restaurants, so that chicken can go from bird to bucket in as little as 48 hours. Some regions operate their own prep hubs, while others rely entirely on in-store breading. Regardless of setup, the steps, the cuts, the brining, the seasoning, the breading method, the pressure fry cycle are replicated with uncanny consistency, batch after batch, store after store. So even though the end product might look simple, a crispy thigh, a golden drumstick, a perfectly breaded breast, it's the result of a highly engineered process that controls every variable, from feedlot to fryer. Every bite of KFC chicken is a small miracle of industrial food science wrapped in proprietary seasoning and delivered at a speed that only automation, logistics, and relentless procedural training can provide. McDonald's burgers may feel like fast food, but behind each patty is a global factory system built for scale, safety, and precision engineering. Millions of burgers are served every single day, and nearly all of them can be traced back to a production process that transforms whole sides of beef into standardized, flash-frozen patties in minutes. At the factory level, making a McDonald's burger isn't about cooking. It's about control of sourcing, fat content, texture, shape, temperature, and microbiological safety. It's meat processing at the scale of aerospace manufacturing. It all starts with the raw material, beef trimmings. McDonald's doesn't use mysterious filler meat or pink slime in its regular burgers. It uses 100% beef, mostly lean trimmings left over after the most valuable cuts, like steaks and roasts, are removed from the carcass. These trimmings arrive at the processing facility in large vacuum-sealed containers, chilled and tracked by batch number and origin. Every shipment is tested before it's even unloaded, scanned for temperature consistency and contamination. Inside the facility, which is refrigerated from wall to wall, the beef moves quickly from receiving to grinding, but not before it's blended. Each patty, whether for a Big Mac, a quarter pounder, or a basic hamburger, has a target fat ratio, typically around 20% fat to 80% lean. Because beef trimmings vary in fat content depending on where they come from on the cow, the factory uses a fat analysis system to create the perfect blend. Optical scanners and near-infrared sensors analyze the fat levels of incoming meat in real time. The system then pulls from different bins of lean and fatty meat and blends them together, like dialing in a recipe by percentage. This blended beef goes into massive grinders, long stainless steel augers that push the meat through ultra-sharp blades, creating a uniform texture. The meat is not overly ground. The goal is to keep the bite structure intact so the patty doesn't become mushy. From here, the ground beef flows into a forming machine, a high-pressure system that presses it into exact size patties using precision molds. Each mold is designed to create uniform diameter, thickness, and weight. For example, a quarter pounder patty is exactly 4 ounces before cooking, while a standard hamburger patty is closer to 1.6 ounces. The forming system presses the meat into a specific density to account for shrinkage on the grill, ensuring that even after cooking, it fits the bun perfectly. But here's where the engineering gets fascinating. McDonald's patties are never seasoned, never pre-cooked, and never touched by human hands once they enter the forming line. The formed patties drop directly onto a freezing conveyor belt, where they're flash frozen at 40 degrees Fahrenheit within minutes. This rapid freezing is crucial. It locks in moisture halts microbial activity, and stabilizes the patty's shape. The faster the freeze, the smaller the ice crystals, which means better texture when cooked later. As patties move through the spiral freezer, they are spaced evenly and continuously monitored by infrared temperature sensors and metal detectors. Any patty that's not perfectly shaped, underweight, or too warm is rejected automatically and diverted for reprocessing. Frozen patties are then stacked into rows by robotic arms and inserted into cartons. These boxes are barcoded, batch-coded, and sealed, then loaded onto pallets for deep frozen storage at 20 degrees Fahrenheit, ready to be shipped to McDonald's distribution centers. Throughout this process, every movement is tracked. Each patty has a data trail that includes time of production, meat origin, grinder settings, fat ratio, freezing time, and packaging line number. Back at the restaurant level, things are equally standardized. Frozen patties arrive in boxes labeled by product type: hamburger, quarter pounder, Big Mac, and are stored in walk-in freezers. When it's time to cook, grill operators pull the exact number of frozen patties needed and place them directly onto clamshell grills. No thawing required. These grills, automated and heated on both the top and bottom, close over the patties and apply uniform pressure and heat. A standard hamburger patty cooks in about 42 seconds. A quarter pounder, which is made from fresh, never frozen beef in some markets like the US, takes slightly longer and is grilled manually in order to preserve texture. The grills are calibrated down to the degree and the cooking time is preset. There's no guesswork, only automation. As the burgers cook, excess fat and moisture drain away through grooves in the grill, while sensors monitor temperature to ensure food safety. Once finished, patties are lifted by the operator and placed into holding trays, where they're kept warm for a maximum of 10 to 15 minutes before being discarded if not served. Another strict quality control rule. No seasoning is added during production. Only salt and pepper are applied after grilling, just before the burger is assembled. This ensures the seasoning is fresh and that the meat surface stays dry enough to achieve the Maillard reaction, giving the patty a browned, flavorful crust. While the patty is the star, the buns are also factory made for exact compatibility. Hamburger buns are baked off-site in high-speed bakeries, cooled, sliced, and flash frozen to lock in moisture. They're toasted at the restaurant on dual contact toasters that heat them to 500 degrees Fahrenheit for just a few seconds, creating a warm surface that resists sogginess and clings to condiments. Each component, from the beef to the bun, is timed, measured, and assembled within seconds at the line. An average McDonald's kitchen can assemble hundreds of burgers per hour, all with patties that are nearly indistinguishable in shape, taste, and texture, because the factories that produce them are engineered to eliminate variation. Sanitation in the patty factory is non-stop. Every surface is stainless steel. Workers wear full body protective gear, pass through air showers, and sanitize hands and boots before entering food zones. All grinders, forming machines, belts, and hoppers are cleaned in place using high-pressure foam and steam sanitation systems. Air is HEPA filtered to prevent microbial spread, and environmental swabs are taken daily for bacterial testing. No part of the system operates without data. Every piece of equipment, from the meat blenders to the freezers, feeds information into a central dashboard monitored by food engineers and safety personnel. If temperatures shift, blade pressure fluctuates, or a batch goes even slightly out of spec, alerts are sent immediately, and the line can be stopped in seconds. Even the sustainability goals are tracked here. Many factories have adopted water recycling, energy-efficient freezers, and methane recovery from meat waste. Trimmings and rejected patties are rendered and repurposed, not wasted. At full capacity, a McDonald's beef patty plant can produce over 2 million patties per day. And despite that staggering number, the quality targets are tighter than many artisanal kitchens. Each burger you unwrap may feel mass-produced, and it is, but it's made in a system where every variable is measured, every motion is repeatable, and the only acceptable outcome is a patty that cooks the same way, looks the same way, and tastes the same way, anywhere in the world. So while the end product may feel fast and disposable, the factory behind every McDonald's burger is anything but. It's a cold, stainless steel symphony of grinding, forming, freezing, and packaging. A controlled ecosystem designed to deliver something incredibly consistent at a scale few other food systems can match. Subway may be known for its made-to-order sandwiches, but the illusion of freshness at the counter is only possible because of a vast, behind-the-scenes production system. One that begins in massive factories designed to produce pre-portioned, pre-baked, and ready-to-build components for every sandwich on the menu. From the foot-long bread to the uniform stacks of meats and sliced vegetables, nearly everything is prepped in specialized food manufacturing facilities that run 24/7 to keep up with the chain's global demand. It all starts with bread, the literal backbone of every Subway sandwich. Despite being baked in-store daily, Subway's bread dough is actually produced in massive bakery plants before ever reaching a restaurant. The factories, often contracted to industrial bakers specializing in frozen dough, mix thousands of pounds of dough at a time, using high-speed spiral mixers and automated ingredient feeders that weigh flour, water, sugar, yeast, and conditioners to tight tolerances. Each type of bread, Italian, 9-grain wheat, honey oat, Parmesan oregano, hearty Italian, and more, has its own dough formula. Once mixed, the dough is divided into loaves using volumetric dough dividers that cut by weight, not by length, to ensure uniform baking later. The portions are gently rolled and shaped into long, narrow sticks on molder conveyors, then deposited onto baking trays. These trays pass through a proofing tunnel, a warm, humid chamber where yeast activates and the dough rises to its final size. But they're not baked yet. Instead, the risen loaves are par-baked, partially cooked just enough to set their structure and kill the yeast. This is done in high-capacity convection ovens running at over 400 degrees Fahrenheit. The loaves spend just a few minutes inside before being cooled with filtered air, then flash frozen on a spiral conveyor. The rapid freeze locks in moisture, preserves yeast flavor, and prevents the crust from hardening. These frozen, par-baked loaves are packed into boxes and shipped in temperature-controlled trucks to Subway locations around the world. At the store level, employees complete the baking in small convection ovens, giving the bread its warm, crusty exterior and that signature fresh-baked smell. But the structure, size, and flavor were all engineered weeks earlier in factories running like clockwork. Next up, meats and proteins. Subway's proteins are not sliced fresh in store. Instead, they're manufactured in large-scale food processing plants where uniformity is paramount. Turkey, ham, and roast beef begin as whole muscle cuts, often sourced from partner suppliers, and flash frozen upon arrival. These cuts are trimmed, brined, and then steam cooked or roasted in industrial ovens that hold hundreds of pounds of meat per batch. Brining is done under vacuum pressure to ensure full absorption of salt and flavor throughout the muscle. After cooking, the meats are chilled rapidly in glycol-cooled tunnels and sent through high-speed slicers, which slice each piece to exact thickness tolerances, usually just under 2 mm. The slices are then stacked and portioned mechanically. For instance, every serving of Black Forest ham is 4 slices, and every turkey portion is 6 slices. These are weighed automatically, with robotic hands inserting them into vacuum-sealed pouches. Each pouch contains a precise, ready-to-use portion, reducing prep time in stores and eliminating the chance of over-portioning. Subway's more processed meats, like cold cuts, salami, pepperoni, and bologna, are made through emulsification and casing processes. Raw meats are ground and mixed with spices and curing agents in vacuum blenders, then extruded into sausage casings or molded into loaves. These are cooked, chilled, and sliced with ultra-thin circular blades, moving at high speed before being packaged in airtight stacks. Then there's chicken, which comes in several forms: oven-roasted breast, grilled strips, breaded patties, and shreds for items like the rotisserie-style sandwich. Chicken breasts are tumble marinated in massive drums, where flavor and moisture are distributed through mechanical agitation. Grilled strips are cooked on conveyor belt broilers, where radiant heat and searing rollers cook both sides simultaneously before cutting into uniform strips. The cooked chicken is then chilled and packed into food service bags with oxygen absorbers to extend shelf life. Protein items, like meatballs and steak, are also made off-site. Meatballs are machine-formed, cooked in steam ovens, and flash-frozen in their marinara sauce. Steak is pre-cooked, sliced, and frozen in bulk bags, often with added broth or seasoning to enhance juiciness once reheated. Nearly all of these proteins are delivered frozen or refrigerated, depending on local food safety laws and distribution times. Subway stores store them in walk-ins or lowboys, where they're portioned and prepared according to daily demand forecasts. What about vegetables? Most are pre-sliced, bagged, and shipped in cold chains from regional produce hubs. Lettuce arrives shredded. Tomatoes, cucumbers, green peppers, and onions are sliced in high-volume produce facilities using industrial slicers that sort by size, color, and ripeness. Carrots are often pre-julienned, olives are pitted and sliced by weight, and pickles come brined and pre-cut. These produce plants, clean, sanitize, and process vegetables in washed zones lined with antimicrobial flooring and ozone-treated water baths. Optical sorters remove subpar pieces before packing. The sliced vegetables are packed in modified atmosphere packaging, MAP, bags, where oxygen levels are replaced with nitrogen and CO2 to slow spoilage. Bags are labeled with time and date stamps and have a strict shelf life, often just 3-5 days. At the store, staff empty these bags into prep bins, which are rotated based on FIFO, first in, first out protocols. While tomatoes and green peppers may be sliced fresh in store in some regions, most of the work has already been done at the factory. Even cheese is precision manufactured. Subway's sliced American and provolone are pre-cut in industrial dairy plants, where large blocks of cheese are sliced using wire cutters or ultrasonic blades, then interleaved with film to prevent sticking. Shredded cheeses like mozzarella or Monterey cheddar are pre-mixed and coated with anti-caking agents before being shipped in sealed bags. Every item is packed to support Subway's global supply chain. Boxes are coded by product, lot number, and production date. QR codes link to supplier details and quality checks. Temperature sensors are built into pallets to detect cold chain failures. Everything from deli meats to banana peppers is logged, scanned, and traceable. Back in the factories, sanitation is near obsessive. All equipment is cleaned in place daily with caustic foaming agents and food-safe steam. Conveyor belts are removable and made from non-porous plastic polymers. Floors are angled for drainage and cleaned hourly. Workers wear full PPE, including gloves, hairnets, beard guards, and gowns. Entry into production zones requires passing through sanitizing air curtains and foot baths. Factory temperatures are tightly controlled. Cold rooms never rise above 41 degrees Fahrenheit. Warm zones like ovens and proofing tunnels are separated by temperature-locking vestibules to prevent microbial crossover. Air is filtered through HEPA systems to remove particulate matter and pathogens. Every food item undergoes microbiological testing, both at the production site and third-party labs. Products are sampled in real time from the line, plated onto culture media, and incubated to check for E. coli, Listeria, or Salmonella. Batches are not released until testing clears. And then there's distribution. Subway partners with a network of food service distributors who move products from regional hubs to stores every 2-3 days. Trucks are loaded using route-optimized software, and each delivery contains just enough to stock the store without overloading fridge space. Bread dough, meats, cheese, sauces, and produce all arrive together, prepped, chilled, and ready for that made-to-order illusion. In truth, the fresh assembly line at Subway is just the final 5% of a process that begins weeks earlier in factories designed for speed, safety, and consistency. Every slice of meat, every loaf of bread, every spoonful of tuna is measured, packaged, tracked, and delivered to make sure that a sandwich made in Omaha tastes exactly like one made in Orlando or Osaka. So while it may seem like your sandwich is made right in front of you, it's really the result of an entire industrial food system humming quietly in the background, mixing dough, slicing tomatoes, marinating chicken, and portioning cheese by the ton. Subway is a global sandwich brand built not just on customization, but on the relentless predictability of factory precision. And every 6-inch sub starts in a facility engineered to make fresh feel effortless. Chef Boyardee beef ravioli begins its industrial journey with the delivery and preparation of raw ingredients in a tightly controlled, high-capacity food processing environment designed for continuous, large-scale output. At the very start, durum wheat semolina arrives in bulk and is stored in tall silos connected by enclosed pneumatic systems that transport measured amounts of flour into industrial mixing vats. These mixers operate under vacuum to prevent air entrapment in the dough, which could compromise the texture of the final pasta. Water is injected through a flow-regulated system, and the dough is mixed into a dense, elastic mass that is then conveyed into a dough sheeter. Inside this machine, large stainless steel rollers gradually press the dough into a long, uniform sheet of precise thickness. Sensors constantly monitor and adjust roller pressure, sheet thickness, and alignment in real time, ensuring consistent dimensional control across thousands of linear feet of pasta every hour. As the pasta sheet continues on its route, it approaches the forming station. Here, the sheet is split into top and bottom layers using a synchronized cutting system, and the beef filling, prepared simultaneously on a parallel line, is introduced between them. The beef mixture is produced in massive steam-jacketed kettles, where ground beef is cooked with tomato paste, spices, salt, and stabilizers. High-shear mixing blades ensure uniform blending, while thermal sensors regulate the internal temperature to avoid overcooking. Once cooked, the beef filling is transferred to positive displacement pumps that feed the filling directly into the ravioli former. Precise nozzles inject a consistent amount of filling at evenly spaced intervals onto the bottom sheet. The top sheet is laid over it, and the two layers are pressed together by a rotary die that seals and cuts the individual ravioli pockets in one continuous motion. Any excess dough around the edges is collected and recycled back into the dough feeder. The freshly formed ravioli travel along a mesh belt through a par cooking tunnel, where a curtain of low-pressure steam partially cooks the pasta just enough to firm the structure and set the seal. The par cooking chamber is followed by a high-efficiency air chiller that quickly cools the product to prevent further cooking. From here, the ravioli move to the accumulation table that feeds the canning line. The tomato sauce, which is made in a separate set of kettles, is already being prepared in parallel. This sauce includes tomato puree, vegetable oil, spices, and sugar, blended in high-capacity vats, equipped with wall-scraping agitators to ensure uniform cooking and prevent scorching. The sauce is filtered to remove any large solids, skins, or seeds, and is kept hot in jacketed holding tanks while waiting to be dispensed. The canning line is a seamless, high-speed process that brings ravioli and sauce together inside sterilized metal cans. Empty cans are first fed from depalletizers into an inverted position for steam or air sterilization before being returned upright and carried along a conveyor. A timed filling system first drops a preset quantity of ravioli into each can. Next, a separate nozzle dispenses a specific volume of hot tomato sauce into the same can. Load cells and vision sensors measure weight and volume in real time, instantly rejecting any can that falls outside tolerance. To maintain long shelf life, the filled cans receive a quick injection of steam into the headspace to displace oxygen, which is critical for preventing spoilage and discoloration. The cans then proceed to the seaming machine, which applies and crimps the metal lids at high speed using rotary chucks that spin and press the lids into place with a hermetic seal. Once sealed, the cans are routed into a massive rotary retort, a large pressure chamber where the canned ravioli undergo commercial sterilization. This thermal processing step is one of the most critical phases in the entire operation. Inside the retort, the cans are exposed to pressurized steam at temperatures above 121 degrees Celsius for a fixed period, calculated according to product density, can size, and altitude. The process is tightly controlled by a programmable logic controller that adjusts heat input, steam pressure, and timing with precision, ensuring that the interior of each can reach the temperature needed to destroy any potential microbial contaminants. This sterilization method allows the product to be shelf-stable for over a year without the use of chemical preservatives. As the cans exit the retort, they are rapidly cooled using a countercurrent water system that brings the internal temperature down quickly while avoiding thermal shock that could warp the can. After cooling, the cans are dried using air knives that blow off any surface moisture. They then move into the labeling area where each one is printed with a unique production code, expiration date, and batch number using high-speed inkjet printers. These codes are logged in a centralized database that allows full traceability of every can, linking it back to the exact batch of dough, filling, sauce, and sterilization cycle. This traceability system is essential for maintaining quality control and complying with food safety regulations. Labels are applied using rotary labelers, which align the cans, dispense the adhesive-backed labels, and press them smoothly onto the curved surfaces. Any can with a misapplied or missing label is automatically diverted off the line. The labeled cans proceed to the packing station, where they are grouped into shrink-wrapped multi-packs or loaded into cardboard trays, depending on distribution requirements. Robotic arms equipped with vacuum suction heads stack these cases onto pallets in a tightly packed, interlocked pattern that ensures transport stability. Each pallet is weighed, stretch-wrapped, and labeled with a scannable barcode that encodes the full logistics data for shipping and warehouse integration. Completed pallets are conveyed into a climate-controlled warehouse area, where ambient temperature is maintained within a narrow range to preserve product integrity and packaging quality. The inventory system automatically logs each pallet into a virtual grid based on product type, batch, and destination. Orders from distribution centers are matched against inventory using software that assigns retrieval instructions to automated guided vehicles. These vehicles transport the pallets to loading bays where they are prepared for shipment on temperature-managed trucks. Throughout this entire process, every step is monitored by industrial control systems that log thousands of data points per minute, from moisture content in dough to the pressure in the retort chamber. If any sensor detects an anomaly, whether it's a filling inconsistency, temperature deviation, or mechanical irregularity, alarms are triggered, and corrective protocols are initiated automatically. Quality assurance technicians also perform random sampling at every stage, testing dough elasticity, filling viscosity, source pH, seam width, and internal vacuum levels. Any sample that fails a parameter prompts an investigation and potential quarantine of the related batch. The design of this factory setup allows for continuous production for 24 hours a day. with modular maintenance schedules that let individual lines shut down without halting the entire operation. Cleaning-in-place systems run through every tank, pipe, and pump at regular intervals, using cycles of hot, caustic solution, followed by acid rinses and pure water flushes. This level of automated sanitation prevents bacterial buildup and maintains a sterile environment, especially critical in the post-cook zones. By the time a single can of Chef Boyardee beef ravioli reaches the supermarket shelf, it has passed through dozens of machines and control checks, undergone multiple thermal transformations, and been assembled from raw materials that were processed, cooked, combined, sealed, and sterilized within minutes of each other. The result is a uniform, shelf-stable product that replicates the exact same taste, texture, and aroma across millions of cans each year, a feat of engineering, timing, and integrated automation performed at industrial scale. The industrial production of gnocchi begins with a continuous intake of raw potatoes selected specifically for their starch content, moisture levels, and uniformity. These potatoes arrive in bulk, often delivered in heavy-duty totes or truckloads, and are immediately transferred into stainless steel receiving bins. From here, a water flume system propels the potatoes toward the washing stage using a circulating stream of filtered water, which not only moves the product gently, but also performs a preliminary rinse that separates dirt, rocks, and field debris. The potatoes pass into a rotary drum washer, a large cylindrical cage lined with soft baffles and rotating paddles. Inside, multiple high-pressure spray jets clean the surface of every tuber, while slow drum rotation ensures even exposure. Wastewater is filtered and recycled back into the flume, maintaining efficiency while minimizing fresh water consumption. Once cleaned, the potatoes move onto inclined conveyor belts and pass beneath an optical sorter that detects misshapen or heavily blemished specimens. Air jets eject any defective potatoes instantly. The remaining load proceeds toward the steam peeling chamber, a sealed environment into which high-pressure steam is injected rapidly. This process loosens the skins in seconds without penetrating deeply into the flesh. A sudden pressure drop follows, causing the skins to rupture. As the chamber releases its load, rubber fingers or gentle high-pressure sprayers remove the loosened skin without damaging the underlying structure. The peeled potatoes then travel along a belt for final inspection before cooking. Next, they enter a cooking tunnel equipped with rotary steam ovens or belt-fed boiling sections. These systems are calibrated to cook each potato evenly, using internal probes to track core temperature without overcooking the starch. The cooking time is precisely tuned so the flesh softens just enough for mashing while preserving structural integrity. Cooked potatoes are discharged directly into screw-fed conveyors that deliver them into industrial mashing systems. These mashers force the hot potatoes through perforated plates using rotating paddles, breaking them into a uniform, lump-free mash with consistent density. This mash is transferred into stainless steel hoppers, fitted with agitators to prevent settling while it awaits mixing. Simultaneously, dry ingredients are prepared using a separate set of feeders. Wheat flour, salt, and any dry seasonings are metered in precise ratios using volumetric or gravimetric dispensers, ensuring repeatable consistency across large batches. These dry components meet the hot mash in horizontal ribbon mixers or twin screw extruders, where the dough is developed. If eggs or other binders are used, these are injected through nozzles timed to match the flow rate of the dry and wet components. Dough temperature, torque, and consistency are continuously monitored, allowing automated systems to adjust mixing speed or ingredient dosing in real time. As the dough reaches its final form, it exits into forming lines. These lines are fitted with multi-head extrusion units that shape the dough into cylindrical ropes, which are automatically guided into a cutting module. Guillotine blades or rotary knives slice the ropes into uniform pillow shapes at high speed. Each piece is then transferred onto a vibrating sorting table to prevent clumping and ensure even spacing before shaping. For traditional gnocchi, a patterned drum or stamp roller presses the surface of each dumpling, forming the signature ridges. These ridges aren't just for appearance. They help hold sauces and ensure the texture is consistent during cooking. The raw gnocchi are now ready for par cooking. Depending on the product type, they may enter a steam tunnel, boiling water bath, or continuous blanching system. For fresh gnocchi, a short steam treatment helps gelatinize the starch on the outer layer, setting the shape without fully cooking the interior. In the case of shelf-stable or refrigerated products, boiling is used for more complete cooking. The gnocchi travel through the system on mesh conveyors that allow water to drain or steam to vent. Those that float prematurely, often indicating trapped air or structural failure, are skimmed off and diverted. Finished gnocchi are cooled rapidly with air or chilled water sprays to stop the cooking process immediately. Cooling is followed by drying. Par-cooked gnocchi are passed through air tunnels or oscillating belts with forced, filtered airflow. This surface drying stage ensures the pieces don't stick together in packaging. In some configurations, a fine coating of semolina or rice flour is applied to further reduce surface tackiness. At this stage, the gnocchi are fully formed, partially cooked, and ready for packaging or freezing depending on the final product category. Fresh gnocchi are directed into multi-head weighing systems that portion exact quantities into pre-formed pouches. These machines calculate the best weight combination from multiple hoppers to ensure precision. Pouches enter a modified atmosphere packaging (MAP) chamber, where the ambient air is replaced with a mix of inert gases like nitrogen and carbon dioxide. This extends shelf life by inhibiting microbial growth and oxidative reactions. Sealing jaws then close each pouch under pressure, forming airtight seals. Pouches exit the MAP system and are immediately inkjet printed with production codes, expiration dates, and batch tracking information. For frozen gnocchi, the cooled pieces bypass MAP and instead travel to the freezing tunnel. This is a long conveyor system housed within an insulated chamber where fans blow extremely cold air across the product. The process is known as IQF, or individual quick freezing, which ensures that each gnocco freezes separately, avoiding clumps. Once frozen solid, the gnocchi are packaged in bulk or consumer-ready bags, sealed, labeled, and sent to deep freeze storage. Regardless of the format, every package goes through a metal detection and X-ray inspection station before final packing. These machines identify any potential contamination from production, like stray metal fragments from worn machine parts, and immediately reject any affected units. Packages that pass inspection proceed to robotic case packers, where arms equipped with vacuum grippers load them into cardboard boxes. The boxes are sealed, barcoded, and sent to automated palletizers that stack them according to optimized loading patterns. Each pallet is stretch wrapped and labeled with a traceable QR code or barcode, then entered into the warehouse management system. The final stage is cold storage and distribution. Refrigerated products are stored at 2 to 5 degrees Celsius, while frozen products are kept at 18 or colder. High-density shelving is managed by ASRS units, automated storage and retrieval systems that navigate the warehouse floor with programmed efficiency. When an order is placed, the system retrieves the correct pallet, stages it at the loading dock, and synchronizes it with outbound transport logistics. Goods are typically moved in temperature-controlled trucks that maintain strict thermal stability to prevent texture loss or microbial growth during transit. Quality assurance labs operate in parallel with the production floor. Technicians pull random samples from each batch to assess moisture content, cooking time, bite texture, and microbiological safety. These samples are cooked and evaluated for structure, flavor retention, and resistance to disintegration. Texture analyzers apply calibrated pressure to measure chew resistance, while high-resolution cameras measure shape retention after boiling. If a batch fails any parameter, the corresponding lot is flagged in the system and held for further review or disposal. Cleaning and maintenance operations take place in modular shifts. All lines are fitted with cleaning in place (CIP) circuits, automated wash systems that flush tanks, hoses, pumps, and valves with caustic solutions, hot water, and acid rinses. This ensures hygienic conditions even when production is running continuously. Key areas like mashing stations, flour feeders, and packing heads receive manual cleaning daily, and critical equipment like extrusion heads are dismantled, brushed, sanitized, and reassembled before every major production run. Throughout the process, every detail is monitored by supervisory control and data acquisition (SCADA) systems. These systems provide operators with real-time dashboards showing dough temperature, flow rates, extrusion torque, cutter speed, par cooking dwell times, and fill weights. Alerts and automated corrections ensure that even minute deviations are caught and resolved without interrupting production. Historical data is stored and reviewed to improve yield, reduce waste, and maintain traceability. From field harvested potato to the final sealed pouch or frozen bag, gnocchi production at factory scale is a precisely tuned sequence of heat, pressure, shaping, and preservation, all balanced to protect the soft, pillowy character that defines this classic product. What begins as humble starch and flour becomes thousands of identical dumplings per hour, delivered with perfect form, flavor, and shelf stability. Lasagna production in a factory is a multi-phase, highly integrated process that combines pasta sheet manufacturing, meat sauce preparation, cheese blending, layer assembly, baking or pasteurization, portioning, packaging, and cold chain logistics, all synchronized to ensure consistency, safety, and scale. Unlike dry pasta or single-element products, lasagna is a fully prepared, multi-ingredient dish. This makes its industrial production uniquely complex, requiring extensive machinery and tightly controlled automation to ensure that every slice mirrors the expected texture, flavor, and structure. The process begins with pasta sheet production. Durum semolina flour is delivered in bulk and stored in silos. From there, it moves through pneumatic conveyors into high-capacity mixing vats where it's combined with water under vacuum. This vacuum mixing reduces air bubbles and improves dough elasticity. The dough is then extruded into wide sheets using continuous sheeting rollers. These rollers compress and stretch the dough between pairs of calibrated rollers, gradually flattening it to a specific thickness, typically less than 1 millimeter. Optical thickness sensors positioned along the rollers feed data into a closed-loop control system that makes micro-adjustments in real time. The continuous pasta sheet is then guided onto a conveyor that passes through a high-temperature dryer tunnel. This dryer uses forced hot air to reduce surface moisture and firm the sheet slightly without fully cooking it, which gives it the pliability needed for layering. After drying, the sheet moves into a cutting system. Depending on the product specifications, a rotary knife assembly cuts the sheet into wide rectangular panels, each aligned with the intended tray dimensions. A rejection arm automatically discards any sheets that are torn, folded, or non-uniform. While pasta sheets are being prepared, the factory simultaneously produces the meat sauce. Ground beef is loaded into steam-jacketed kettles equipped with high-speed agitators. The meat is seared first, breaking it into small crumbles. Tomato puree, tomato paste, oil, chopped onions, garlic, herbs, and seasoning are metered into the kettles through automated valves. The sauce is simmered while being agitated to prevent scorching and ensure uniformity. During this time, Inline temperature probes and brick sensors monitor thickness, sugar levels, and viscosity. Once the sauce reaches its target consistency, it's pumped through heated stainless steel pipelines into holding tanks that maintain it at a constant temperature until assembly. In a separate mixing area, the cheese component is prepared. Depending on the recipe, this may include a blend of ricotta, mozzarella, and parmesan. Ricotta is delivered in cooled totes and mixed with stabilizers, herbs, and sometimes eggs in vertical mixers to ensure even distribution. Shredded mozzarella and grated parmesan are stored in silo-like hoppers connected to vibratory feeders that portion out cheese by weight for each layer. Now begins the core of the lasagna production, layer assembly. This takes place on a continuous assembly line with moving trays or belt-mounted mold forms. Each tray or mold is sanitized prior to filling and travels under a set of ingredient dispensers. First, a measured amount of meat sauce is deposited into the bottom of the tray by a servo-controlled nozzle that moves in a sweeping pattern to ensure full coverage. A vacuum depanner then places a single pasta sheet on top, aligning it precisely over the sauce. This is followed by a ricotta deposit nozzle that pipes a uniform, ridged bead of cheese across the sheet, which is then smoothed by a vibrating spreader bar. Another pasta sheet is placed, and the cycle repeats: sauce, pasta, cheese, until the required number of layers is achieved. The top layer typically ends with sauce and a sprinkling of shredded mozzarella and parmesan dispensed by oscillating auger heads that shake cheese evenly over the tray surface. Before baking or pasteurization, some lines include a brief compression station where a flat paddle gently presses down on the lasagna to remove air pockets and improve bonding between layers. The fully assembled trays then move on to the thermal treatment phase. If the lasagna is intended to be frozen, the thermal step may be pasteurization, which involves heating the product just enough to kill bacteria but not fully cook it. For chilled or ready-to-eat versions, full baking is performed. Trays enter a convection oven that circulates heated air at over 180 degrees Celsius. The line speed, tray height, and internal oven temperature are all controlled to ensure even cooking from edge to center. Internal temperature probes inserted in sample trays verify that core temperature targets are achieved and held for a specific time to guarantee food safety. Once cooked or pasteurized, the lasagna must be cooled rapidly to prevent microbial growth and lock in texture. This is done through a tunnel chiller, where trays pass through zones of progressively colder air, sometimes supplemented by glycol-cooled plates that pull heat from the tray bottoms. The cooling process must reduce the product from over 80 degrees Celsius to below 5 degrees Celsius within a few hours, which is regulated by airflow, dwell time, and temperature differential. Sensors at the tunnel exit confirm that each tray meets cooling requirements. Once cooled, the lasagna is portioned and packaged. If individual servings are required, the tray is sliced by ultrasonic knives that vibrate at high frequency, cutting cleanly through dense layers without dragging or distortion. For family-sized portions, the entire tray may be sealed as is. Packaging formats include vacuum-sealed trays, film-sealed thermoformed, packages, or sealed and labeled foil trays, depending on the target market. Modified atmosphere packaging may also be used for chilled products to extend shelf life. Oxygen levels are flushed and replaced with inert gases before the final seal is applied. Each sealed package passes through a metal detector and X-ray unit to ensure it contains no foreign materials. It then receives an inkjet printed label showing the batch number, production date, expiration date, and a scannable code for traceability. The labels are verified by vision systems to confirm placement, readability, and correctness. Any mislabeled unit is automatically rejected into a separate channel. From there, packages are grouped into boxes using robotic case packers. These cases are palletized by automated arms that stack them in stable formations, alternating layers for weight distribution. Stretch wrapping units seal the full pallet, and each is tagged with a warehouse tracking code before being moved to cold storage. Depending on the product type, it may be stored in refrigerated or frozen conditions. Pallets are managed by automated guided vehicles that transport them to pre-assigned racks in high-density storage systems, where inventory software tracks position, age, and destination. Throughout this process, the factory uses a SCADA, supervisory control, and data acquisition system to monitor every critical variable. Dough hydration levels, pasta sheet thickness, sauce viscosity, cooking times, and packaging seal integrity are all tracked in real time. Historical data is stored and analyzed to identify patterns, correct deviations, and optimize throughput. If any parameter falls outside the designated range, alarms are triggered, and the system automatically isolates affected batches for inspection. Cleaning and sanitization cycles are embedded throughout the plant. Clean-in-place systems run through the pasta extruders, sauce kettles, and piping lines at scheduled intervals. Belts, mixers, and conveyors are cleaned using automated foamers and high-pressure rinsers between production runs, often overnight. This ensures the plant can shift from producing meat lasagna to vegetarian or gluten-free variants without cross-contamination. Every few hours, quality assurance teams perform manual inspections of randomly selected trays, assessing factors such as layer adhesion, ingredient distribution, flavor profile, pH level, and slice integrity. Cooking tests are conducted to see how the product behaves in a domestic oven or microwave, ensuring the consumer experience matches factory standards. The entire process, from flour and raw meat to finished boxed lasagna, is designed for speed, consistency, and hygiene. Trays of lasagna move continuously through a loop of automation, blending traditional culinary elements with industrial engineering. The meat must be savory but not greasy. The pasta should remain tender after reheating without breaking apart. The cheese should melt and set without seeping or becoming rubbery. Each of these qualities is maintained not through guesswork but through precise mechanical control over every movement, temperature change, and ingredient ratio. Spaghetti production in factories begins with the precise blending of durum wheat, semolina, and water in massive stainless steel mixers that rotate at controlled speeds to ensure uniform hydration. The semolina used is specially milled to have a coarse texture that provides the ideal structure for pasta, unlike finer flours used in bread or cakes. Water is added in exact ratios, typically around 30 to 33% by weight, to activate the gluten without making the dough too sticky or too dry. The mixing process takes approximately 15 to 20 minutes, during which sensors monitor temperature and moisture levels to prevent overheating or uneven consistency. Once the dough reaches the right consistency, it is fed into a vacuum deaerator that removes trapped air bubbles, preventing imperfections during extrusion. This vacuum step is critical because air pockets can cause the spaghetti to break or cook unevenly later in the process. The dough then enters a twin screw extruder, where hydraulic pressure forces it through bronze or Teflon dies with hundreds of tiny holes arranged in precise circular patterns. Bronze dies are preferred for traditional pasta because they create a slightly rough surface that holds sauce better, even though they wear down faster than Teflon. Each die is engineered to produce strands exactly 2 millimeters in diameter, with tolerances of less than 0.05 millimeters to maintain consistency across entire production runs. As the dough is extruded, it emerges as continuous strands that are immediately cut into standardized lengths of 25 to 30 centimeters using high-speed rotating blades. The cut strands are gently guided onto moving conveyor belts made of food-grade polymer that prevent sticking while allowing airflow underneath. These belts carry the spaghetti into the first drying chamber, where temperature is held at 35 degrees Celsius, and humidity is kept below 60% to begin slow moisture removal. Drying is not a single-step process. It occurs over 4 to 6 hours across multiple zones, with gradually decreasing humidity and increasing temperature. In the initial drying zone, moisture is slowly drawn from the outer surface of the strands to prevent cracking or surface hardening. The second zone raises the temperature to 45 degrees Celsius while reducing relative humidity to 40%, allowing moisture to migrate from the core outward. In the third zone, the temperature climbs to 55 degrees Celsius and humidity drops to 30%, accelerating the drying of the pasta's interior without collapsing its structure. A final conditioning zone at 30 degrees Celsius and 55% humidity allows the pasta to equilibrate, ensuring even moisture distribution throughout each strand. Throughout the entire drying process, robotic arms with infrared sensors continuously scan each batch for cracks, warping, or discoloration, automatically diverting defective strands. After drying, the spaghetti is cooled in a controlled environment to room temperature over the course of 90 minutes to prevent condensation and microbial growth. Cooling is done with filtered, dehumidified air to avoid reintroducing moisture that could lead to spoilage during packaging. Once cooled, the strands are gently shaken and separated by vibrating screens that disentangle any strands that may have adhered during drying. A powerful air stream then blows away any residual semolina dust or small fragments that could affect texture or shelf life. The spaghetti is then fed into precision weighing systems that portion out exact quantities, typically 500 grams or 1 pound, into food-grade polypropylene bags. Each bag is sealed with heat, creating an airtight barrier that protects against oxygen, moisture, and pests for up to 2 years. Inside the sealed bag, a small oxygen absorber packet is often included to further extend shelf life by eliminating residual oxygen. Before sealing, a metal detector scans each package to ensure no foreign materials, such as metal fragments from machinery, have contaminated the product. The packaged spaghetti is then labeled with batch numbers, expiration dates, and nutritional information using high-resolution inkjet printers that operate at speeds exceeding 100 packages per minute. Each label is scanned and logged into a centralized digital tracking system that links every box to its exact production time, raw material source, and quality control checkpoints. The boxes are stacked by robotic arms onto pallets, wrapped in stretch film, and moved via automated guided vehicles to a climate-controlled warehouse. The warehouse maintains a constant temperature of 18 degrees Celsius and humidity below 50% to preserve the pasta's texture and prevent mold. Before shipment, random samples are pulled from each batch and sent to an on-site laboratory for microbiological testing, including checks for Salmonella, E. coli, and mold spores. The lab also performs texture analysis using a texture analyzer that measures the firmness of cooked spaghetti to ensure it meets the industry standard al dente criteria. Each batch is tested for cooking time, with the target being 8 to 10 minutes in boiling water, and deviations trigger an automatic review of the drying parameters. Once cleared, pallets are loaded onto refrigerated trucks that maintain a steady 10 to 15 degrees Celsius during transit to prevent thermal degradation. The entire production line operates 24 hours a day, 7 days a week, with only brief scheduled maintenance windows to clean and inspect critical components. Every hour, the extruder dies are manually inspected and cleaned with high-pressure steam to prevent bacterial buildup in the microscopic holes. The mixing tanks are sanitized with food-grade citric acid solutions after every batch to eliminate cross-contamination risks between different pasta shapes. Workers in the facility wear full hairnets, gloves, and shoe covers, and all entry points have air showers that blow away dust and particles before entry. The factory's HVAC system filters air 15 times per hour, maintaining a Class 8 clean room environment to meet international food safety standards. All equipment is designed with smooth, seamless surfaces and no crevices where dough or debris could accumulate and become a breeding ground for microbes. Robotic vision systems monitor the color and shape of every strand exiting the extruder, rejecting any that deviate from the established visual profile. If a strand is found to be too thick, too thin, or irregularly shaped, the system automatically adjusts the extrusion pressure in real time to correct the issue. The factory produces over 12 million kilograms of spaghetti annually, enough to feed approximately 200 million servings per year. Each kilogram of finished spaghetti requires precisely 1.1 kilograms of semolina, with the remaining 0.1 kilogram lost to moisture evaporation during drying. The water used in production is filtered through reverse osmosis systems to remove minerals that could affect dough texture or flavor. Wastewater from cleaning is treated in an on-site biological filtration plant before being safely discharged into municipal systems. Used semolina dust is collected and sold to livestock feed manufacturers, reducing waste and contributing to a circular economy model. The energy used in drying is partially recovered through heat exchangers that capture exhaust heat and reuse it to preheat incoming air. The factory's lighting system uses motion-activated LED panels that dim or turn off in unoccupied zones to reduce electricity consumption. Every machine on the line is connected to a central AI monitoring system that predicts maintenance needs based on vibration patterns and motor load. This predictive maintenance reduces unplanned downtime by over 40% compared to traditional scheduled servicing. The factory's quality control team includes food scientists with PhDs who regularly test new semolina varieties and drying algorithms to improve efficiency. New production runs are always preceded by a trial batch that undergoes sensory evaluation by trained tasters who assess texture, aroma, and mouthfeel. Each factory worker undergoes quarterly food safety certification and participates in simulated contamination drills to maintain readiness. The entire process, from raw semolina to sealed box, takes less than 7 hours from start to finish, making it one of the most efficient food manufacturing systems in the world. No preservatives are added to the spaghetti, relying entirely on low moisture content and airtight packaging for long-term stability. The final product contains no cholesterol, no saturated fat, and no added sugar, making it a nutritionally neutral staple in global diets. Every strand of spaghetti produced in this facility is identical in diameter, length, density, and cooking behavior to the one before it, thanks to relentless automation and real-time feedback systems. The factory operates with zero tolerance for human error in the final packaging stage, as even a single mislabeled box could trigger a nationwide recall. Lasagna production in factories starts with a dense, coarse semolina flour blended with chilled, purified water in a slow-turning horizontal mixer that prevents overdevelopment of gluten. Unlike spaghetti dough, lasagna dough is formulated to be slightly drier and more rigid, enabling it to hold its shape during stacking and baking without becoming soggy. The water used is pre-cooled to 12 degrees Celsius to maintain dough temperature below 24 degrees during mixing, preserving the natural starch gelatinization profile. After blending, the dough is rested for 15 minutes in a sealed, humidity-controlled chamber to allow gluten strands to relax and absorb moisture evenly. This resting phase is critical. It reduces the risk of sheet cracking during the subsequent rolling process by allowing internal tension to dissipate. The dough is then fed into a tandem roller system composed of hardened steel cylinders that compress the dough in 7 incremental passes, each reducing thickness by only 0.08 millimeters. The final roller gap is set to 0.62 millimeters, producing sheets so uniform that laser sensors can detect deviations as small as 0.01 millimeters across the entire width. As the sheets emerge, they are immediately swept by a gentle stream of dry, filtered air to prevent adhesion to the metal conveyors and to initiate surface drying. The sheets are not cut immediately. Instead, they travel continuously along a 30-meter long drying track suspended above a series of radiant infrared heaters. These heaters emit targeted wavelengths that dry the top and bottom surfaces at different rates, minimizing curling and warping caused by uneven moisture loss. Humidity sensors embedded in the drying tunnel adjust airflow in real time, maintaining a gradient that pulls moisture from the core outward without forming a hard outer shell. Every 12 seconds, a robotic arm lifts a section of the continuous sheet and tests its tensile strength by gently stretching it between calibrated claws. If the sheet fractures or elongates beyond 12% of its original length, the system flags the batch and adjusts the next dough batch's hydration level automatically. Once dried to a moisture content of under 10%, the sheets are cooled in a tunnel filled with recirculated, sterile air to prevent reabsorption of ambient moisture. At this stage, the lasagna sheets are still flexible enough to be handled without breaking, but too brittle to be rolled back into dough. A high-speed cutting station then slices the continuous ribbon into individual rectangles using tungsten carbide blades that operate at 1,200 cuts per minute with zero blade wear. Each piece is precisely 10.2 centimeters wide and 15.5 centimeters long, sized to fit standard commercial lasagna pans and retail packaging dimensions. After cutting, the pieces are lifted by electrostatic air knives that use controlled static charges to separate and align them without physical contact. They are then conveyed over a vibrating platform that gently shakes off residual semolina dust, which is collected and recycled into animal feed. The sheets pass through an ultraviolet sterilization chamber that eliminates surface microbes without altering taste, texture, or nutritional value. Each sheet is individually inspected by a machine vision system that scans for color consistency, surface texture, and the presence of any embedded foreign particles. Defective pieces are ejected into a waste bin using compressed air jets, while acceptable sheets continue to the packaging line. Packaging occurs in a sterile environment where each lasagna sheet is placed into a pre-formed, food-grade cellulose tray lined with a moisture barrier film. The trays are sealed under vacuum with a heat seal lid that creates an airtight barrier, extending shelf life to 18 months without preservatives. Inside each sealed tray, a small silica gel packet is inserted to absorb any residual moisture that might develop during transit or storage. Before sealing, each tray is passed through an X-ray scanner that detects metallic contaminants, plastic fragments, or glass particles invisible to the naked eye. Every package is labeled with a unique QR code linked to its production batch, ingredient source, and quality assurance logs accessible via manufacturer portals. The sealed trays are stacked by robotic arms onto pallets wrapped in heat shrink film, then moved by autonomous guided vehicles to climate-controlled storage. Storage rooms maintain a constant 16 degrees Celsius and 45% relative humidity to prevent brittleness or microbial growth over extended periods. Random samples are pulled daily and sent to the in-house lab for cooking tests, where technicians measure rehydration time, firmness after boiling, and sauce absorption rate. The target is for each sheet to absorb exactly 45 milliliters of water in 8 minutes of boiling, achieving a texture that remains firm yet pliable under cheese and sauce. Lasagna sheets are never pre-cooked. Their dry state is intentional, allowing consumers to layer them directly into casseroles without blanching. The entire production line runs continuously, processing over 800,000 sheets per hour, with each machine synchronized to within 0.01 seconds of the next. Maintenance is performed during scheduled 15-minute windows every 4 hours, during which steam jets clean every surface the dough contacts. No lubricants are used on any part of the machinery that touches the dough. Instead, food-grade silicone coatings are applied to rollers to prevent sticking. All personnel entering the production area must pass through an airlock chamber that blows away particulates before entry, and gloves are changed every 30 minutes. The factory's ventilation system filters air 22 times per hour, maintaining a particulate count lower than that of a hospital operating room. Every batch of semolina is tested for protein content before use, with only flour yielding 12.5 to 13.2% gluten accepted for lasagna production. The water used is reverse osmosis, purified and mineral balanced to ensure consistent dough behavior across different regional water sources. Wastewater from cleaning is treated with activated carbon and UV sterilization before being reused for non-food contact purposes like floor washing. Unused semolina dust is sold to organic fertilizer producers, and packaging film scraps are recycled into industrial plastic pellets. Energy recovery systems capture heat from the drying tunnels and redirect it to pre-warm incoming water, reducing overall energy consumption by 37%. AI algorithms analyze vibration patterns in the rollers and predict bearing failures up to 72 hours in advance, eliminating unscheduled downtime. Each lasagna sheet is designed to expand by no more than 3% when cooked, ensuring layers remain flat and evenly distributed in the finished dish. No additives, preservatives, or enzymes are used. Only semolina, water, and time. The final product contains 0 cholesterol, no trans fats, and less than 0.1% sodium, making it suitable for dietary restrictions worldwide. Each sheet is identical in weight, thickness, and cooking behavior to every other sheet produced in the last 10,000 batches. The factory produces enough lasagna sheets annually to assemble over 50 million individual lasagna dishes, each one ready to be layered, baked, and served. Once packaged, the trays are loaded onto refrigerated trailers that maintain a steady 8 to 12 degrees Celsius during transit across continents. Noodle production in factories begins with the careful selection of high-protein wheat flour, often blended with egg solids or alkaline salts, depending on the regional style being manufactured. Unlike pasta, many noodle varieties require the addition of kansui, a mineral solution of potassium and sodium carbonate, to achieve their characteristic yellow hue and springy texture. The flour and liquid ingredients are mixed in a vertical spiral mixer that gently folds the dough rather than kneading it aggressively, preserving delicate gluten networks. The mixing process lasts only 10 to 12 minutes, as prolonged agitation would overdevelop gluten and make the noodles too chewy or tough. Once combined, the dough is immediately transferred to a resting chamber where it sits under a weighted lid for 20 to 30 minutes, allowing hydration to complete and proteins to relax. This resting phase is non-negotiable. It enables the starch granules to swell fully, ensuring even cooking and preventing mushiness later in the process. After resting, the dough is passed through a series of precision rollers that flatten it into a continuous ribbon, each set reducing thickness by just 0.05 millimeters to avoid tearing. The final ribbon is typically 1.2 millimeters thick, but this varies slightly depending on whether the noodles are intended for ramen, udon, or instant cup varieties. As the ribbon exits the rollers, it is lightly dusted with rice flour or cornstarch to prevent sticking, avoiding wheat-based flours that could alter flavor or cooking behavior. The sheet then moves onto a perforated conveyor belt, suspended above a low-temperature drying zone that begins moisture removal without hardening the surface. Celsius flows upward through the belt. Spam canned meat begins its manufacturing process with chilled pork cuts entering the initial reduction line, where rotating blade assemblies slice the dense blocks into manageable segments that can feed smoothly into the primary grinder. The grinder's helical screw immediately draws these pieces forward, pressing them through a precision-drilled plate that creates uniform meat particles. And this uniformity allows the next mixing stage to distribute additives consistently. These freshly ground particles move directly into a temperature-controlled mixing chamber, whose jacketed walls circulate coolant to maintain a low and stable temperature, ensuring that the proteins do not smear or break down during agitation. As the ground meat settles inside the chamber, automated ingredient dispensers positioned above it release a measured sequence of salt, curing elements, sugar, and additional stabilizing agents, and the moment these ingredients fall in, a pair of interlocked ribbon paddles begins a slow, synchronized rotation designed to pull material from the outer walls toward the center. This inward folding pattern repeats continuously, which gradually builds a uniform matrix of meat and dissolved additives, and that uniform matrix prepares the mixture for vacuum treatment. Once the system's sensors detect that mixing torque has stabilized, an indicator of proper consistency, the vacuum lid seals over the chamber and the air extraction pump begins lowering internal pressure. As the pressure drops, microscopic bubbles rise from the paste and collapse on the surface, and this removal of trapped gases compacts the mixture into a dense, cohesive phase that will later hold its shape inside the can. When the vacuum cycle completes, hydraulic actuators tilt the entire mixing vessel forward, guiding the meat paste toward a stainless steel discharge chute. This chute leads the paste directly onto an enclosed transfer conveyor whose internal airflow is tightly controlled. And this enclosure prevents temperature fluctuations as the paste moves toward the portioning system. As the conveyor delivers the mixture into the depositor's intake manifold, a series of metering cylinders opens to receive it, each cylinder equipped with a sliding gate and a vertically driven piston. These cylinders fill one after another until integrated load cells confirm that each chamber holds the exact programmed mass, and once this mass is reached, the sliding gates close to isolate the measured portions. Meanwhile, empty cans advance along a parallel conveyor that narrows into single-file alignment, and as they move, they pass through filtered air jets that clear their interiors of loose dust or microscopic particles. This preparation ensures that when the cans reach the filling zone, each one is ready to receive its measured charge of meat paste without interference. The two conveyors meet at the depositor, where each can is precisely positioned beneath a cylinder's outlet by a mechanical indexing arm that pushes the cans into perfectly spaced pockets along the line. As soon as a can reaches the correct location, the piston above it begins its downward motion, forcing the compact meat paste into the metal cavity in a single continuous stroke, which eliminates voids and establishes the characteristic block-like internal structure. When the piston retracts, a fixed wiper blade scrapes the cylinder's interior surface to prevent residue buildup, and this ensures that every subsequent portion enters the next can with the same exact mass and texture. Once filled, the cans transition onto a settling conveyor equipped with a low-frequency vibration plate. This plate applies gentle vertical oscillations to the freshly filled cans, allowing the paste to settle and eliminate microscopic gaps that may still remain after piston filling, and the stabilized contents prepare the cans for immediate sealing. As the cans leave the settling area, they enter a high-speed seaming machine, where a pre-formed metal lid is dropped precisely onto each rim, while a rotating chuck and roller assembly crimps the lid's edge into the can body. This forming operation creates a gas-tight double seam, and the uniformity of this seam is essential for the next major phase, thermal processing. Once sealed, the cans enter a continuous retort system, a long, tunnel-like chamber where steam or superheated water circulates around rotating baskets that hold the cans. As the baskets move, every can experiences consistent heating, and this heat penetrates the dense meat block, activating the curing reactions and stabilizing the proteins while rendering the final texture. The retort maintains precise time and temperature conditions so that each can reaches the target internal temperature at the correct rate. And this controlled heating transforms the formerly soft paste into the firm, sliceable form associated with the product. When the thermal cycle ends, the cans exit the retort and immediately enter a cooling zone where chilled water sprays reduce their temperature in stages, preventing sudden contraction that could deform the seam. After cooling, the cans move onto an air drying conveyor, where high-velocity fans remove surface moisture to prepare them for labeling. The dry cans then enter the labeling carousel, which applies adhesive-backed wraps that align perfectly using optical registration sensors, ensuring each label sits squarely against the cylindrical surface, without wrinkles. As the labeled cans rotate through the carousel, pressure rollers press the labels firmly to guarantee complete adhesion and a smooth exterior finish. Once labeling is complete, the cans advance toward the inkjet coding station. Here, a high-resolution nozzle prints alphanumeric production information onto the top or bottom surface of each can. The printer synchronizes its spray pulses with the conveyor's exact speed so each code lands consistently in the same position. Immediately after printing, a short section of forced air nozzles dries the ink before the cans make contact with any guiding rails, preventing smudging during the remainder of the line. With coding complete, the cans reach the final inspection conveyor. A series of sensors check seam integrity, label placement, fill height, estimated through weight readings, and can dimensions. Any can falling outside the allowed tolerance triggers an automated pusher arm that diverts it from the main flow. The accepted cans continue onward to the packaging assembly, where they enter a carton forming machine. This machine erects flat cardboard blanks into open cartons using vacuum grippers and folding rails. And once the cartons hold their shape, the cans slide into them in tightly organized rows. As the cartons fill, an overhead flap folder closes the top panels while a gluing station applies a thin line of adhesive. Compression belts then squeeze the cartons briefly to activate the bond. The sealed cartons immediately transition to a palletizing system. This system arranges the cartons layer by layer onto large pallets using a pattern that maximizes vertical stability during transport, and each layer aligns precisely with the next through mechanical guides that keep the arrangement square. Once the pallet reaches its programmed height, a wrapping arm encircles it with stretch film, stabilizing the entire load for movement. The finished, fully wrapped pallets then roll onto the outbound conveyor, completing the transformation from raw pork cuts to fully processed, thermally stabilized, sealed, labeled, coded, and packed canned meat. Smoked salmon begins its manufacturing process with whole chilled fillets entering the trimming line, where a synchronized set of blade assemblies removes the thin belly membrane and levels the surface of each fillet to create a consistent starting geometry. This geometry is crucial because it determines how evenly the salt mixture will absorb later. So immediately after trimming, the fillets slide onto a conveyor that positions them for the pinbone extraction machine. Here, a series of narrow oscillating grippers aligns over the muscle surface, gripping and lifting each pinbone in a single upward pull. This extraction eliminates hard points that could interrupt the uniform curing and slicing process downstream. Once trimmed and deboned, the fillets enter the curing section. A volumetric salt dispenser releases measured layers of salt and sugar over the conveyor belt, and the fillets pass beneath its nozzles, so each surface receives an exact dosage. As soon as the salt mixture makes contact, a mechanical arm flips each fillet to coat the opposite side, ensuring symmetrical curing. The salt crystals immediately begin drawing moisture from the muscle fibers, and this moisture migrates toward the surface, dissolving the crystals into a brine layer. To control this reaction, the fillets move into a stacked curing tunnel. In this tunnel, multiple perforated trays hold rows of fillets while a constant airflow passes over them. This airflow pulls excess moisture away and maintains a stable environment, allowing the muscle proteins to tighten and form the firm, translucent texture associated with smoked salmon. As curing progresses, the brine that forms on each fillet drains into collection channels beneath the trays. These channels lead to a filtration chamber where the liquid's density and conductivity are measured. Although the brine is discarded, the sensor data ensures that each batch reaches a consistent cure level before exiting the tunnel. When the curing cycle finishes, the trays slide onto an outbound lift that lowers them to the rinsing line. Here, a set of low-pressure water jets washes the residual surface salt from the fillets without disrupting the internal gradient created during curing. The water jets oscillate side to side, covering every region of each fillet. After rinsing, the fillets pass through an air knife dryer, where high-velocity sheets of air remove excess surface moisture and prepare the flesh for the drying stage. The dried fillets enter a dehydration chamber equipped with long horizontal racks that move forward in slow increments. Within the chamber, controlled heat and airflow create a narrow humidity band that gently reduces water activity. This step tightens the muscle structure even further, which allows smoke particles to adhere more effectively later. As the fillets travel through the chamber, internal moisture equalizes from center to exterior. By the time they exit, each fillet has reached the ideal pre-smoking firmness. Immediately after dehydration, the fillets pass into the smoking system. This system is a multi-zone chamber divided into sections that control smoke density, airflow direction, and temperature independently. The first zone introduces a thin, mild smoke created by controlled smoldering of hardwood chips inside a sealed generator. The smoke enters through overhead ducts and spreads evenly across all racks. As the fillets move forward, they encounter the second zone, where smoke density increases and recirculating fans push air diagonally across the racks to ensure complete surface exposure. Temperature remains low, so the flesh does not cook. Instead, the smoke compounds slowly bind to the proteins, forming the glossy outer layer characteristic of smoked salmon. The final smoking zone shifts airflow to a vertical pattern. Fans pull smoke downward across the fish, penetrating any microgrooves in the muscle surface. The chamber's sensors track particulate levels continuously, adjusting feed rates so each batch receives consistent exposure. By the time the fillets exit the smoking chamber, they exhibit a uniform color gradient and a stabilized texture that can withstand mechanical slicing. The smoked fillets then travel to a brief cooling tunnel, where chilled air circulates around them to halt further smoke absorption. The cooling also firms the muscle, which enables cleaner cuts in the slicing stage. As each fillet cools, it is transferred onto a wide conveyor that feeds into the slicing preparation unit. This unit aligns fillets lengthwise using adjustable side guides. Once aligned, an overhead scanner maps the fillet's dimensions, determining thickness variations that could influence slicing pressure. With dimensional data collected, the fillets advance toward the horizontal slicer. This machine uses a rapidly vibrating blade or multi-blade band system that creates thin, even slices with minimal pressure. The oscillation speed keeps the blade from dragging through the flesh, producing smooth surfaces. As the blade moves, each slice falls gently onto a receiving belt positioned below the fillet. This belt is coated with a non-stick surface, so slices do not fold or stretch. A secondary belt intersects at a shallow angle and transfers the slices in a neatly fanned arrangement. This arrangement maximizes visibility and uniformity for packaging. Once sliced, the salmon enters the portioning zone. Laser-guided weigh cells determine how many slices make up the programmed portion weight, and conveyor actuators separate the slices into exact groups. These portions move forward onto chilled stainless steel plates that stabilize the slices while the vacuum packager prepares the film. Above the plates, a sheet of high barrier film unwinds between two tension-controlled rollers, maintaining consistent thickness and preventing wrinkles. The plates then slide beneath the film, and the chamber closes over them. Inside the vacuum packager, air is extracted from the sealed chamber, causing the film to drape tightly over the salmon slices. Once vacuum reaches the set value, a sealing bar applies heat around the pack's perimeter, bonding the film to the lower tray. The chamber then releases, and the packages exit onto a cooling conveyor, where cold air vents help the sealed film re-harden and maintain shape. After cooling, the packages move beneath a printer that adds production codes and traceable identifiers in a uniform location. With coding complete, the packages travel through an inspection array. Multiple sensors evaluate seal integrity by measuring how the film reflects laser light. If any section deviates from the expected pattern, the system flags the package and removes it from the line. The remaining packages continue toward the cartoning machine. This machine erects cardboard sleeves and inserts the sealed packs into them using sliding rails. The sleeves close around the packs, forming rigid, stackable units. The carton packs then advance to a shrink-wrapping tunnel. Here, a thin layer of polymer film forms a tight secondary wrap around multiple cartons at once, stabilizing them for palletizing. The film shrinks under warm air jets and contracts uniformly around the load. Next, the stabilized multi-packs reach the palletizer, where mechanical arms lower each group into a structured pattern on a pallet deck. Once enough layers accumulate, a rotating arm dispenses stretch film to lock the full pallet together. Returning to the earlier stages, the process can be understood as a continuous sequence where each transformation prepares the salmon for the next. For example, the trimming ensures clean edges that allow salt to contact evenly. The curing step modifies water distribution across the flesh, increasing firmness so the fillets can tolerate the dehydration chamber's airflow without warping. Dehydration, in turn, creates a surface environment ideal for smoke absorption. Smoke exposure produces a protective exterior that both contributes flavor and stabilizes the fillet for slicing. That stabilized texture then enables the slicing blades to glide without tearing, producing aesthetically consistent pieces. Packaging locks in these qualities by removing oxygen and sealing moisture, and the final palletizing step ensures the product remains structurally stable during distribution. Each component in this chain depends on the previous one functioning precisely. For instance, the air knife dryer, before dehydration, removes free water that would otherwise block smoke adhesion. The scanner before slicing collects geometric data that allows the slicer to adjust blade angle and oscillation speed. The laser seal inspection verifies that vacuum packaged trays maintain internal negative pressure, preventing unwanted changes to texture. Even transitions between steps contribute to consistency. Conveyors connecting curing, rinsing, drying, smoking, and slicing maintain uniform spacing and synchronized speed so fillets never bunch or overlap. In the smoking system, airflow patterns shift gradually, ensuring that smoke density changes do not shock the fillets and cause uneven absorption. Cooling tunnels introduce chill in stage temperature bands, preventing rapid contraction of the smoked flesh. Further upstream, the curing tunnel's brine drainage pattern ensures that salt contacts both sides of each fillet evenly over time. The perforated trays allow moisture to escape uniformly, reducing pooling that could disrupt the curing gradient. Downstream, the slicing portioner uses real-time weight calculations to maintain consistent package weights, even if individual slices vary slightly in thickness, due to natural variations in the fillet. Finally, each process concludes by stabilizing what the previous one created. Curing stabilizes moisture, drying stabilizes texture, smoking stabilizes the exterior protein structure, cooling stabilizes slice quality, and vacuum packaging stabilizes the final product against environmental changes. Chicken breasts begin their manufacturing process as chilled, whole muscle portions move from bulk bins onto the initial alignment conveyor, where parallel guide rails orient each piece in the same direction to prepare them for precision trimming. The trimming machine uses a series of synchronized rotary blades that contour along the natural shape of the breast, removing residual skin, excess fat, or uneven edges, so the muscle presents a consistent thickness for all downstream steps. As each trimmed piece leaves the blade assembly, it transitions onto a weigh belt, whose integrated load cells capture mass data in real time, allowing the system to sort the breasts toward different processing paths based on their size profile. Once sorted, the chicken breasts advance to the surface inspection module. Overhead, scanners emit a structured pattern of light that maps each fillet's geometry, measuring thickness, curvature, and moisture sheen. The resulting data determines how the fillets will be oriented for the tenderization stage. The conveyor adjusts its speed to ensure spacing between fillets, keeping each breast centered beneath the next mechanical unit. When a fillet reaches the tenderizer, two opposing roller heads covered with evenly spaced protrusions lightly compress the muscle fibers. This compression standardizes texture and promotes even absorption during subsequent marination. Directly after tenderization, the breasts enter the injection system. Here, a horizontally oriented manifold holds dozens of thin, hollow needles aligned in a grid pattern. As the fillets pass beneath them, the conveyor pauses momentarily while the needles descend into the muscle. Pressurized pumps deliver a calibrated solution, often containing water, salt, and functional ingredients, through the needles into the interior of each breast. The injection system monitors internal pressure to prevent overfilling and ensures that the distribution remains uniform throughout the muscle. When the needles retract, the conveyor restarts and sends the breast toward the tumbling drums. The tumbling drums rotate slowly around a horizontal axis, their interior surfaces lined with lifting baffles that scoop and drop the chicken repeatedly. This tumbling motion distributes the injected solution evenly and allows the muscle fibers to relax, improving texture. The drums operate under vacuum, removing trapped air from between muscle layers and enhancing the efficiency of the tumbling action. As the drum completes its cycle, a discharge door opens and the breasts slide onto a perforated conveyor where excess liquid drains away before the next processing stage. Following tumbling, the breasts enter a flattening system designed to create uniforms, thickness across all pieces. Two parallel belts run through a narrowing gap, pressing each breast gently but firmly as it passes. Sensors above and below the belts measure compression force and automatically adjust the belt spacing. This guarantees a uniform surface thickness, which will later allow consistent thermal processing and slicing if required. Once flattened, the fillets move towards the portioning unit. The portioner uses a combination of vision scanning and dual blade cutters to segment each breast into precise shapes or weights, depending on the intended final product. For example, a large breast may be divided into multiple uniform cutlets. The scanning system builds a 3D model of each fillet's profile, determining the optimal cutting lines for maximum yield. Rotary blades then execute each cut, while the fillet is kept motionless by a short vacuum hold on the conveyor. The cut pieces drop onto a secondary belt that organizes them into rows for further processing. At this point, the breasts may undergo surface seasoning. A dry ingredient applicator deposits an even curtain of powdered seasoning across the conveyor. The fillets pass beneath the curtain, where the powder adheres to the slightly tacky surface left from the tumbling process. A vibrating platform beneath the belt helps distribute the seasoning uniformly, preventing clumping. An air knife station then removes excess particles, ensuring consistent coverage. Next, the breasts enter the forming and shaping line. This system uses a high-pressure forming chamber to shape pieces into standardized contours if the product requires precise geometry. The breasts slide into molding cavities created inside a chilled forming plate, and a top plate descends to apply uniform pressure. The muscle conforms to the cavity shape, and after a brief hold, the mold opens, pushing the shaped portions onto a release belt. This shaping improves the predictability of cooking and slicing patterns later. From shaping, the chicken breasts move toward the thermal treatment area. The first step is preheating, where the fillets pass through a controlled warm air tunnel that brings their surface temperature to a precise range. This prevents shock when they enter the main cooking chamber. The preheated breasts continue onto a multi-zone oven with separate temperature and airflow controls. The first zone rapidly increases internal temperature through forced convection. The second zone stabilizes the temperature rise to prevent overcooking on the exterior. The third zone holds the chicken at its target core temperature long enough to achieve structural firmness. Inline temperature probes mounted on robotically positioned arms insert into sample breasts at intervals to verify that the oven settings align with the internal heating model. These probes transmit data instantly to the oven's control module, which adjusts airflow, humidity, and heat output to ensure uniformity across the entire batch. As the cooked breasts exit the oven, they enter a rapid cooling tunnel where chilled air streams across both sides of the fillets to lower their temperature quickly, locking in texture and preventing residual cooking. If the product requires slicing, the cooled breasts drop onto the slicing conveyor. A high-speed blade assembly cycles through several thousand oscillations per minute, producing clean cuts with minimal pressure. The slicing unit uses sensors to map each breast surface and adjust blade angle to maintain consistent thickness across every slice. As slices fall onto the belt below, they arrange automatically into overlapping shingled patterns using a series of angled guide plates. This pattern makes packaging easier and ensures visual uniformity. If the product remains whole, the breasts bypass the slicer and continue toward the surface freezer. This system uses extremely cold air circulated at high velocity to chill the outer layer of each fillet just enough to stabilize its shape. This process, known as crust freezing, prevents deformation during packaging and helps maintain the precision of portions created earlier. Once properly cooled or crust frozen, the breasts enter the packaging line. Here, they move into a vacuum sealing machine equipped with multiple forming pockets. Each pocket holds a single breast or sliced portion. The bottom film pulls tightly into the pocket to create a tray-like shape, and the chicken breast settles into this molded film. A top film then drapes over the product, and the chamber closes. Air extraction creates a vacuum that tightens the film around the product. A heat seal bar bonds the edges of the film layers, locking the product inside an oxygen-reduced environment that preserves texture. After sealing, the packages travel along a cooling belt to allow the film to contract evenly. The next station is the print coder, where inkjet nozzles apply product information and production identifiers onto each package. Optical sensors verify print legibility and alignment. Packages with misprints are diverted by a pneumatic pusher arm that only activates for items exceeding the coded tolerance. The accepted packages then move into the inspection unit. X-ray scanners evaluate internal density to identify bones or foreign matter. Because chicken breasts vary naturally in density, the scanner uses an adaptive algorithm tuned to muscle structure. Any package showing an anomaly is removed automatically. Approved packages proceed toward the carton loader. The carton loader erects flat cardboard blanks into open containers using mechanical folding arms. The vacuum-packed chicken slides into these cartons via a sloped feeding chute, and adhesive applicators seal the top flaps. The cartons then pass through a bundling station where they group into sets. A shrink-wrap film encircles these groups, and they enter a heat tunnel where warm air shrinks the film tightly around them. Once bundled, the cartons advance toward palletization. A robotic arm lifts each bundle and places it onto a pallet following a precise stacking pattern optimized for stability. Layer by layer, the stack grows until it reaches the programmed height. When complete, an automated stretch wrapper encircles the entire pallet with a spiraling sheet of film that secures the load.